Question belongs to the subject Digital Logic Design and the topic name is K-map and it was asked in GATE CSE 1992. So the question states, the Boolean function is sum of products form where K-map is given below is. So here we are given the two variable K-map and we need to find the SOP form for this K-map. But remember one thing, whenever we are given a K-map, we have variables over the edges and we have zeros and ones inside. But here you can see the variable a is present inside. So we need to first expand this K-map into a three variable K-map. So let me first draw the diagram for this given K-map. For this given K-map for B and C, we will have an output. So for 0, 0, 0, 1, 1, 0, 1, 1. So what is the output? See, for 0, 0 we have 1, for 0, 1 we have 0, for 1, 0 we have A complement, and for 1, 1 we have A. Now let us make this into a three variable K-map. So here we have three variables A, B and C. Its values can be 0, 0, 0, 0, 1, 1, 0, 1, 1 with all zeros, or it can be 1, 0, 0, 0, 1, 1, 0 and 1, 1 with all ones. So what can be the output? So see, B and C are 0, 0. If B and C are 0, then the answer is 1. So B and C are 0, irrespective of A, answer is 1. B and C are 0, irrespective of A, answer is 1. B and C are 0, 1, then irrespective of A, answer is 0. For 0, 1, answer is 0. For 0, 1, answer is 0. For 1, 0, answer is A complement. So for 1, 0, answer is A complement, which means 0 complement means 1. 1, 0, answer is A complement, which means 1's complement, which is 0. For 1, 1, answer is A. For 1, 1, answer is A, which means 0. For 1, 1, answer is A, which means 1. Now let us draw the K-map for this. So we will have a three variable K-map. 1, 2, 3, 4. So we will have A over here, BC over here, and the values will be 0, 0, 0, 1, 1, 1, 1, 0, and here we will have 0, 1. See, for 0, 0, 0, let me take a different color. For 0, 0, 0, it is 1, and 1 is for 0, 1, 0, 0, 1, 0, it's 1, okay, and 1 is present for 1, 0, 0, 1, 0, 0, it's 1, okay, and then 1 is there for 1, 1, 1, 1, 1, 1, we have 1, okay. Now let us see. So let us try to draw the couplings. So here we can have this one pair. So the output F will be, for this pair it will be, this will cancel out and we will have B complement, C complement. Okay. Then we will, this won't pair with anything. So for this we will have ABC. For this we can have single, but 2 is also possible. This can pair with this. And here the answer will be A complement. And over here and here, this 0 and 1 will cancel out and we will get C complement. So the answer is ABC plus A complement C complement plus B complement C complement. This question belongs to Digital Logic Design subject and the topic name is Parity Bits or the Error Detection and Correction Methods, and it was asked in GATE CSE 1991. So the question states, consider a 3-bit error detection. So error detection, we have 3-bit error detection and 1-bit error correction. So error correction, we have 1-bit error correction. Hamming codes. All is done using Hamming code method. Hamming codes. For a 4-bit data is a 4-bit, okay. The extra parity bits required would be, so here we are having a concept of parity bits, even parity and odd parity. So they are used for error detection and correction. So it is asking how many parity bits are required. And a 3-bit error detection is possible because this error detection 3-bit is possible because the code has a minimum distance of, so we have something called as Hamming distance. So it is called asking for the Hamming distance. What is the minimum Hamming distance possible? Okay. So let me first tell you some basic things. Okay. So what is a Hamming distance? So Hamming distance is the number of bits by which two strings differ, or we can say it is the distance between two binary strings is the number of bits that would have been flipped to make the strings identical. Like if we have 110 and 100, then we just need to flip this bit so they have a Hamming distance of 1. And if we have 100 and 111, then we need to flip this bit and this bit to convert this to this, thus Hamming distance is 2. So I have given you the definition for the Hamming distance. Now see, for detecting d-bit errors, we require a Hamming distance of C. For d-bit error detection, Hamming distance required is d plus 1. Okay? These things you need to remember. And for error correction, for d-bit error correction, the Hamming distance required is 2d plus 1. Okay? Where what is d? D is the number of bits. Okay? Now see. Now let us answer this question. It is asking for the number of parity bits required. Okay. So we have a formula for this. So the formula is given something like this. D plus P plus 1 should be less than equal to 2 to the power P. Where what is D? D is number of data bits. What is P? P is number of parity bits. Now let us see. What are the number of data bits? We have 4 data bits. What is the number of parity bits? We do not know. Is less than equal to 2 to the power P. Okay. So as we have P and P, let us do it by hit and trial method. Let us assume P to be 2. Okay. And see. 4 plus 2 plus 1 is less than equal to 2 to the power 2. Which means 8 is less than equal to 4. Which is wrong. So P can't be equal to 2. Let us see P equals to 3. So 4 plus 3, 7 plus 1, 8 is less than equal to 2 to the power 3. 8 is less than equal to 8, which is correct. Thus, the number of parity bits required would be 3 parity bits. So parity bits required are 3. Okay. Now let us see the second part. So second part is saying what is the minimum Hamming distance required. Okay. So we know for our error detection of 3-bit, here I have told you minimum Hamming distance for a d-bit error detection is d plus 1. Okay. For d-bit error detection, Hamming distance is d plus 1. So here, what is the Hamming distance? Here, d is 3. Okay. See, we have a 3-bit error detection. So the answer would be d plus 1. The Hamming distance would be d plus 1. So what is d? Here d is the number of bits for which detection is done, and here d is the number of data bits. Here d is the number of data bits, and here it is the number of bits for which error detection or correction is done. So for 3-bit we have 3 plus 1 equals to 4. So the answer is minimum Hamming distance is 4. Let me tell you all the things once again. We have an error detection on 3-bit error detection. We have 1-bit error correction. Data is a 4-bit. So we need to find number of parity bits and minimum Hamming distance. So minimum Hamming distance for d-bit error detection equals to d plus 1, and for d-bit error correction equals to 2d plus 1. Hamming distance is the number of bits by which we can make a shift to make the two binary strings equal. Okay. Now see, if we have d as number of data bits and p as number of parity bits, then we have a formula this. You just need to remember this formula, and this formula. Then we put to p equals to 2, it do not satisfy. P equals to 3, it satisfies. So minimum parity bits are 3. Then we use this formula to find the number of, for 3-bit error detection, what are the number of minimum Hamming distance. So minimum Hamming distance for 3-bit is 3 plus 1, which is 4-bit Hamming distance is minimum. So answer is 4. The answer is 3 and 4. This question belongs to the subject computer organization and the topic name is microprocessors. It was asked in GATE CSE 1992. So the question states, many microprocessors have a specialized lower limit on the clock frequency. Apart from the maximum clock frequency limit, because. Okay. So what is a frequency? We know frequency equals to 1 upon time. Okay. Now we have a limit, specialized lower limit. So what happens when frequency reduces? So when frequency reduces, then time period increases. So why do we have a limit on the minimal frequency or the maximum time period, or in which an operation can occur? We have this limit because, see, we have RAM. RAM is a volatile memory. So whatever data is present over here in the form of bits, it is basically lost after a period of time. And to maintain this data, we basically need to provide some current over here. A charge is being provided so as to retain the data. And if this time period increases beyond the time of this volatility, like it has some limit, let us suppose 10 microsecond, after which we will lose this charge. So we need to provide the charge again. And if this time is more than 10 microsecond, let us suppose 12 microsecond, then we will lose this data in the RAM. So we need to make sure that our frequency is such that the time limit is less than this 10 microsecond. Thus, we have a lower limit for the frequency, as we need to keep a upper limit for the time so that it is within the time of this recharge. This question belongs to the subject computer organization and was asked in GATE 1992. So the question states, many of the advanced microprocessors prefetch instructions and store it in an instruction buffer to speed up processing. This speed up is achieved because, okay. So let me tell you the scenario. So what happens, suppose we have a CPU and we have a memory. Let us suppose in RAM only, we have our instructions written over here. Suppose CPU wants to get an instruction. So what happens, CPU has to make the request to get the instruction, go to the RAM and get the instruction. So there is some time required for this getting this instruction, and these buffers are very slow. As the time this, we know this memory speed is very less than CPU speed. See, memory speed is very less than CPU speed. So let us suppose it takes 10 seconds to get an instruction, 10 millisecond, let us suppose 10 milliseconds to get an instruction. This time is very much high for the CPU, as the CPU is operating at a very high frequency. So for this 10 milliseconds, CPU has to remain idle. So what is the solution for this? We prefetch this instruction and store it in a buffer. And this buffer has a very low access time. We can say it has a very high speed of transfer. Thus, CPU can access this data now at a very high pace and it do not have to wait. So, because to reduce waiting time. So, to reduce waiting time, we basically prefetch the instructions in the instruction buffer from the process, from the RAM. So, we have done to reduce the waiting time. This question belongs to computer network subject and was asked in GATE CSE 1992. So the question states, a simple and reliable data transfer can be accomplished by using the handshake protocol. It accomplishes reliable data transfer because for every data item sent by transmitter. Okay, so we have something called TCP handshake protocol. So whenever a client and a server wants to send some data, they basically have some connection request or some data that they share. So it is asking, it is reliable data transfer. Why it is called a reliable data transfer? Let me show you the diagram for this TCP handshake protocol. So what happens is that, suppose this is our host P and this is our host Q, or a client and a server. Then first of all, this client sends a sequence number along with a synchronization request. It tells that it wants to transfer the data. As host sees this request, it generates its own sequence number and sends this sequence number along with a synchronization request. Okay, and it sends the acknowledgement for this sequence number. So if it was 10, then it sends a number 11, which is 10 plus 1. Okay, so acknowledgement equals to 11. Okay, so which means for each request it is sending an acknowledgement, which means it is reliable because receiver sends acknowledgement, or we can say confirmation of receipt of data, which means it sends a acknowledgement that it has received the data. Now what happens here? We have got acknowledgement equals to 11. So now we send another acknowledgement. So we acknowledge for this frame. So acknowledgement number equals to the sequence number. Let us suppose sequence number was 20. Then we send acknowledgement equals to 21. So why is it reliable? It is reliable because we are sending a confirmation for every data item that we have received. This question belongs to computer organization subject and was asked in GATE CSE 1992. So the question states, in an 11-bit computer instruction format, the size of address field is 4-bit. The computer uses expand output technique and has a 5 two-address instruction and 32 one-address instructions. The number of zero address instruction it can support is okay. So we have a instruction of size 11 bits. So what are the number of encodings? Number of instruction encodings possible. It is equals to 2 to the power n or 2 to the power 11, or we can say it is equal to 2048 instruction encodings are possible. Okay. It has a 4-bit address field. Now it is using expand opcode technique, 5 two address instructions. Two address instruction means we have address 1 and address 2. Let us suppose we have add register R1 to R2. So what it does, it adds R1 and R2 and stores in R1. This is a two address instruction. So how many encodings can be possible? Number of two address instruction encoding. We have 5 two address instructions. What is the size taken by one address? It's 4. So number of encoding is 2 to the power 4 because of one address and 2 to the power 4 because of another address. Like it will take 4 bit and it will take 4 bit. So total is 8 bit. So it is equals to 2 to the power 4 into 2 to the power 4, or we can write 2 to the power 8 directly. So the number of encodings are 1280 instruction encoding. Now we have 32 one address instructions. So let us suppose something like add A1, add R1. So is increment adds the value of R1 to the value of accumulator and stores it in accumulator. Okay, so number of one address instruction encoding equals to only 32 are there. Okay, and what is the size taken? We have an opcode and an address. So address size is 4 bits. So into 2 to the power 4. So we get it to be equal to 512 instruction encoding. So this total, let us suppose this is A. A should be equal to B plus C plus D. And what is D? D is number of zero address instruction encodings. So what is A? It's 2048. Total should be equal to 2 address plus 1 address plus 0 address. So D equals to 2048 minus 1280 minus 512. So what is it equal to? It is equal to 256. So number of 0 address instruction encodings are 256. So the answer is 256 0 address encodings. So what is a 0 address encoding? We just have an opcode and no operand is there. Like let us suppose we have an INCR instruction. If no operand is there, then the address is by implicitly defined in the instruction itself. So it will increment the accumulator value. Okay, so the 256 is the answer. This question belongs to computer organization subject and was asked in GATE CSE 1992. So the question states, macro expansion is done in pass 1 instead of pass 2 in a 2-pass macro assembler because. So let me first tell you the history behind this. So suppose we have a program. Now during our program, it may be possible that we are using some large name or we are using an expression. suppose there is an okay, let us assume we are using the value of pi. So pi value is 3.141. So instead of using 3.141 inside our program, we want to use the symbol pi. So here we will use the macro expansion. So here we will define a macro pi and its value to be 3.141. Or we can also define an expression like a, the expression is 3 plus 2 minus 4 plus 6. Anything we can define as a macro. So this is a macro. Now what happens? Whenever inside our code we will use the pi, but then we need to do this macro expansion. So macro expansion means replacing this pi with its value, which is 3.141. So all these values will be replaced. But there is a problem in this. The problem is forward reference problem. I will tell you what the issue is. The issue is, let us suppose we are having our code and we have pi over here. But due to some jump statements, we have defined pi after this. Let us assume it to be like this. Like we have a define over here, but before define we have jump over here, and here we have define called pi. So this is forward reference problem, and we need to deal with this problem. As well, when we come to this pi, we do not know that it is a macro. So how we will deal with this problem? We will deal with this problem using two passes, pass 1 and pass 2. So what happens in pass 1? In pass 1, we will do the first reading of the assembly program. So one reading will be done, and we will convert it into an intermediate form. And store it in memory. And what happens in pass 2? In pass 2, it is made over this intermediate form. The pass 2 is made over this intermediate form, and here we will be using a symbol. We will creating a symbol table which will tell us like pi, it has a value 3.141. And in pass 2 we will be using this. So what happens in pass 1? So pass 1 basically does two tasks: defining the symbols and the macro expansion. Because basically we have a macro and we basically need to convert it into its equivalent form according to its definition, and it is done in the pass 1. It contains defining the symbols like this in the table and the macro expansion, which means replacing pi with the value 3.141. This is the work of, that is why macro expansion is done in the pass 1 instead of pass 2 in a 2-pass macro assembler. This question belongs to computer organization subject and was asked in GATE CSE 1992. So the question states, the purpose of instruction location counter in an assembler is. So suppose we have some code over here, and in code we have assembly level language. Now the assembly level language will have various instructions like move something to R1 to R2. It will have various mnemonics, and there will be some terms like go to, because in the normal code we have if statements, we have certain while loops, we have for loops. So for these statements we need to write the go to statements and the address over here. Let us suppose go to X. But during the compilation phase, when we are reading, then we do not know what is the address of this X. So we keep a track that we need to assign some address to the X. And during the first pass, and during the second pass we actually get to know what is the address of that location X, and during the second pass we fill the particular address over here. The address A1 is filled over here. So this is called backpatching. So what does the instruction location counter holds? An instruction location counter is basically used for this backpatching work, and it holds what is the next available address that needs to be assigned to a particular instruction so that it can help us in the backpatching work. This question belongs to algorithm subject and was asked in GATE CSE 1992. So the question states, complexity of Kruskal algorithm for finding the minimum spanning tree of an undirected graph containing n vertices and m edges if the edges are sorted is. So what is a spanning tree? A spanning tree is nothing but it is a subgraph of a graph, minimal subgraph of a graph which is a tree, is a tree. So what is the meaning of tree? A tree means it should be non-cyclic. It should be non-cyclic. And a spanning tree generally has all the vertices, which means V vertices, and number of edges E equals to V minus 1. Now there can be many spanning trees possible. Suppose if this is the graph and the vertices are 10, 20, then we can have over here 30, 40, 50, and this is 60. So we can have various spanning trees like this one, or we can have like this one, but the cost will be different. This will have cost 10, 20, 10, 30, 20. So its cost is 60, and this one cost is 10, 50, 40. So its cost is 100. So the finding the spanning tree for which the cost will be minimum is called the MST problem. So MST can be done either by Kruskal-Algo or by Prim's-Algo. Okay, so what Kruskal-Algo says? Kruskal-Algo says each time get minimum weighted edge. So let us try to do it so that there is no cycle formed. So for this, what is the minimum weighted edge? Let us draw the vertices. So minimum weighted edge is 10. Now next minimum is 20. Okay, next minimum is 30. So this is our Kruskal algorithm, and in each step we need to make sure that there is no cycle formed. In this question there was no cycle formed by default, but if it was something like this, we have 10 over here, 20 over here, then we have something as, okay, let us suppose we have something 10 over here, we take this, then we have 20, so we take this, then we have 20 over here, so we take this, then we have, yeah, let us take the graph to be like this. We have 10 over here, we have 20 over here, we have 30 over here, then we have 40, then we have 50, and then we have 60 over here. So first of all we take the minimum is 10, okay, then we take the next minimum, it's 20, then next minimum 30 is forming a cycle, so we do not take it, and we take the next minimum, which is 40. So in this case MST is 70. Okay, so this is the Kruskal algorithm. So it is asking what is the complexity of Kruskal algorithm if all the edges have been sorted. Like we do not need to sort the edges, we can directly pick them up. So in the case when all the edges have been sorted, then Kruskal algo, so this is a Kruskal algo, will basically boils down to the union find algo. Union find. Kruskal is basically done using union find, but we also need to sort. So how the algo will look like? Algo will look like something for each edge UV in our graph G. We will find if the find set, which is the particular set to which edge U is present, is not equals to find set of V. If they have different find sets, then we will do union of U and V. What's the complexity of this? The complexity of this equals to alpha into number of vertices. This alpha is called the inverse Ackermann function. Okay, and it's approximately equals to order of the number of vertices. Order of log number of vertices. Okay, this alpha v has a value equals to this. So for each edge, so how many edges do we have for? So for each edge, we are doing this. What's the complexity for each edge? We are doing log v into log v into log v. So what's the acronym for E? It's the number of edges. So here we have m edges, and the number of vertices are n. So answer is order of m log n, which is basically finding the union find for all the edges of the graph. This question belongs to engineering mathematics subject and was asked in GATE CSE 1992. So the question states, Maximum number of edges in a planar graph with n vertices is. So what is a planar graph? A planar graph is any graph which can be represented on a plane such that no two edges should cross each other. So like this one is a planar graph as no two edges are crossing each other. This one is a planar graph. This one is also a planar graph as this edge can be redrawn like this with no two edges crossing each other. And then we have a graph like this one is planar, this is planar as of now, but this one is non-planar. So it's asking for n vertices. What are the number of edges in a planar graph? So assume that number of vertices are n, number of vertices is n, number of edges is m, and number of faces are f. So we have an Euler formula which says number of vertices minus number of edges equals to 2 minus number of faces, or we can write it as n minus m plus f equals to 2. Now see, here we can make an assumption that the number of vertices is greater than equal to 3. Okay, as for 2 vertices, it's a trivial case only. Okay, so now see, as number of vertices are greater than equal to 3. So what is the case that we can't make a new face? So if we are having a triangle, then we can't have a new edge, which means every face must be a triangle. If it is not a triangle, like if it is a square or any other shape, then we can basically have one more extra edge. So to have maximum number of edges, each face should be a triangle. Okay, else we can basically divide each of the face with an S to get a triangle. Okay, and as we know that each edge borders two vertices, this edge borders this vertex and this vertex, thus we can write 2m equals to 3l, as each face, each edge border two faces. Okay, now let us put the value over here, n minus m plus f. What is the value of f? F is 2m by 3 equals to f. 2m by 3 equals to 2. Now we can have it n minus m by 3 equals to 2, or n minus 3n minus m equals to 6, or m equals to 3n minus 6. So this is our answer. For maximum number of edges, the answer is 3n minus 6, as each edge should be a triangle. So we have 2m equals to 3m, and we put it in this formula to get m equals to 3n minus 6. This question belongs to Digital Logic Design subject and was asked in GATE CSE 1992. So the question states, the operation which is commutative but not associative is AND, OR, XOR and NAND. So suppose we have an operation like star, then it is commutative if A star B equals to B star A, and it is associative if A star B star C with A and B in parenthesis equals to A star B star C with B and C in parenthesis. So if you want a shortcut, then just remember that all the operations are commutative. All are commutative. All logic gate operations are commutative. Which means what all operation we have? We have AND, OR, NOT, then we have NAND, NOR, we have XOR, and we have XNOR. So all of them are commutative. Talking about associativity, all are associative except NAND and NOR. I will prove you this. Okay, so first let's see how NAND and NOR are not associative. So we have A, NAND, B. See, what is a NAND operation? NAND operation is AND complement. So A NAND B equals to this, NAND C equals to this. And then we have, this is this one, and then we have A NAND B NAND C. So B and C is and complement, then A comes over here, it becomes like this. Now according to De Morgan's law, A plus B whole complement is A complement into B complement, and A into B whole complement is A complement plus B complement. So we can write it as A dot B whole complement plus C complement, and the second part is A complement plus B dot C whole complement whole complement. Both these complements cancel out. Then we have this equal to A into B plus C complement, and this one equal to A complement plus BC. Let us draw the truth table for both. So we have A, B and C, then A dot B plus C complement and A complement plus BC. So if we have 0, 0, 0, 0, 0, 1, 0, 1, 0, what's the value of A into B? It's 0, 0 plus 0 complement is 1, so it comes out to be 1. A complement is 1, so this one will come out to be 1. We have A into B 0 plus C complement is 0. A complement is 1. So here only you can see that both are giving different values. Thus, NAND is not associative. Now let us see NOR. So for NOR, we just have a plus in place of a dot. We just have a plus and a dot in place of a plus. So we have A plus B double complement, and it comes out to be dot plus C complement, A complement dot, and we have B plus C double complement. Double complements cancel out. So we have A plus B into C complement, and we have A complement into B plus C. Now let us see the values of this. So we have over here A plus B into C complement, we have A complement into B plus C. So for a value 000, we have A plus B as 0, C complement as 1, so it comes out to be 1. We have A complement as 1, 1 into B plus C it's 0, so it comes out to be 0. And here also A plus B is 0 into 0 complement is 1, so it comes out to be 0. We have A plus B as 0, so it comes out to be 0. We have B plus C as 1 and A complement as this, so this comes out to be 1. Okay, see. We have A plus B as 0, C complement is 0, 0 into 0 is 0. Here we have B plus C as 1, 0 complement is 1, so this comes out to be 0, 1. So here both are different. So NOR is also not associative, but they are commutative. You can verify it. So answer is NAND. NAND and NOR are not associative. This question belongs to Digital Logic Design subject and was asked in GATE CSE 1992. So the question states, all digital circuits can be realized using only XOR gate, multiplexers, half adder and OR gates. So what are these all logic gates? So all logic gates are AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate and XNOR gate. Okay, so we have something called functionally complete logic gates. So what is a functionally complete logic gate? Any logic operation which is used to derive any of all the all these 7 operations is called a functionally complete logic gate. So we have NAND, NOR, a multiplexer or a mux and a half adder. So only these 4 are functionally complete, which means suppose we have a half adder, then using this half adder we can make any of these gates, AND, OR, NOT, NAND, NOR, XOR and XNOR. Same with all these 3. So answer is mux, half adder, NAND, NOR. So NAND, NOR are not in option. So answer is option B and C. This question belongs to Computer Organization subject and was asked in GATE CSE 1992. So the question states, bit slice processors can be cascaded to get any desired word length processor. Speed of operations independent of the word length configured. Do not contain anything equivalent of program counter in a normal microprocessor. Contain only the data path of the normal CPU. So what is a bit slice processor? So it's basically an older technology which was used for processing some data. See, this is the Wikipedia information that you can get regarding this. Let us analyze it. So bit slicing. Bit slicing is used in bit slice processors. It's a technique for constructing a processor from modules of processor of smaller bit width. So we have certain processors of smaller bit width. Let us suppose they each of them have 1 bit width, and we have n such processors. So we logically combine these processors to form a n bit width processor. Now see, for the purpose of increasing the word length. So here we have increased the word length from 1 to n. In theory, to make an arbitrary n-bit CPU or a processor, each of these component modules process 1-bit field or slice of an operand. So if we have n-bit operand, then each processor will process 1 bit of the operand so that we can combinedly process all the n bits. The grouped processing components would then have the capability to process the chosen word length of given software design. So it's nothing but generally combining the all the bits to process a n-bit processor, or the smaller word length to process a larger word length. So can be cascaded to get any desired word length processor. Yes, this is true. Let us see option B. Speed of operation is independent on the word length configured. No, this one is false. Speed of operation depends on the word length that is configured. Do not contain anything equivalent to the program counter in a normal processor. No, this one has a program counter, or else how will you keep track of the next instruction to be executed? Contain only the data path of a normal CPU. No, this one is also false. So answer is option A. This question belongs to computer organization subject and was asked in GATE CSE 1992. So the question states, PCHL is an instruction in 8085 which transfers the content of register pair HL to PC. This is not a very commonly used instruction as it changes the flow of control in rather unstructured fashion. This instruction can be useful in implementing if-else then construct, while construct, case construct, or call construct. So let us see what is this PCHL instruction. So what it does is that it loads the HL contents to program counter. And what is this HL? HL is nothing but it is a register pair. Register pair. We have H register and an L register having some data in it. So we load this data into a program counter such that the lower order bits will have L data and the higher order bits will have H data. So what is a program counter? Program counter stores the address of next instruction to be executed. So what we get by this? So basically we have H and L register. We load their value into program counter, which means H and L will have a memory address. We load it into program counter, which means, and program counter stores the address of next instruction to be executed, which means the next instruction will be to be executed will be indicated by HL. Thus, this PCHL is used for unconditional branch. Unconditional branch means we won't see any condition like if will have some condition, while will have some condition, even case statements will have some condition. We will have case x, case y, case z. They will also have some condition. So it will be used for unconditional branch statements where we will transfer the control to the address indicated by HL where register. So if then else will have a condition, while will have a condition, case will have a condition, but call won't have a condition. In call, we do not see any condition, we do not see any check any expression, and we directly transfer the control to this HL pair. This PCHL can be used for call construct. So answer is option D. This question belongs to computer network subject and was asked in GATE CSE 1992. So the question states, start and stop bits do not contain any information but are used in serial communication for error detection, error correction, synchronization, and slowing down the communication. Okay. Suppose we have various hosts and we are sending a message from host A to host B. Okay. We do not use a global clock because it might be possible that a clock time at A is different from a clock time at B. Okay. Thus, in order to maintain the synchronization, and to know which is the starting of a frame and which is the ending of the frame, we will use the start of the frame and end of the frame delimiters. They are basically the patterns or the bits which tells here is the frame is starting and till here the frame is going on. So we use start and stop bits to get to know where is the start and end of the frame and for the synchronization purpose. So the answer is option C. This question belongs to theory of computational subject and was asked in GATE 1992. So it states, which one of the following problems is not NP-hard? Hamiltonian circuit problem, zero-one knapsack problem, finding bi-connected components of a graph, and the graph coloring problem. So let us see each of them one by one. Let V be the number of vertices in a given graph G. We have a graph G with V as number of vertices and E be the number of edges in the graph G. Okay. Now, what's the first problem? It's a Hamiltonian circuit problem. So the time complexity for the Hamiltonian circuit problem is n square into 2 to the power n, where n is the number of vertices. And hence you can see it's not polynomial, it's an NP-hard problem. Even the Hamiltonian circuit problem can be polynomially time reduced to 3 satisfiability problem. And as we know that 3 satisfiability problem is NP complete, therefore Hamiltonian circuit problem is also NP complete. And as it is NP complete, thus it is also NP hard. Okay. Thus the first problem is NP hard. Let us see the second problem. The second problem is zero-one knapsack problem. So the complexity for knapsack problem is n into number of weights, where W is the size of the knapsack and n is the number of items. There are two types of problem. First one is decision problem and the second one is optimization problem. The decision problem is NP complete and the optimization problem is NP hard. Okay, NP hard, which means its resolution is at least as difficult to the decision problem, and there is no polynomial time algorithm which can tell whether a given solution is optimal or not. Thus, it is an NP hard problem. Okay, let us see option C. So option C states finding the bi-connected components of a graph. So you can see to this Wikipedia algo. This algo has been given in the Wikipedia. So it's basically related to how to find the number of bi-connected components. It's basically based on depth first search of the graph. So what's the complexity of depth first search? Is order of V plus E. Thus it is a polynomial time algo and not NP hard. C. It's not NP hard. Now let us see option D. So option D states the graph coloring problem. Let me first clear this out. So option D is graph coloring problem. Okay. So what's the complexity for graph coloring problem? See. See, in graph coloring problem, we given a graph G, we need to color it with the minimum number of colors. Okay. So the graph coloring problem is an NP complete problem, as it is asking for the existence of a coloring with less than equals to q colors, and q is the chromatic number of that graph. Okay, the asking for the existence can be checked easily in polynomial time whether or not it uses less than equal to q colors. So given a coloring, we can check whether it's q colorable or not in a polynomial time. But the graph coloring optimization problem which aims to find a coloring with minimum number of colors, it's an NP hard problem. So optimization problem is NP hard problem, as we need to find a coloring with a given number of colors. Okay, and that should be the minimum coloring, minimum number of colors. Okay, so this is an NP hard problem. So option D is also NP hard, A is NP hard, B is NP hard. Option C is only polynomial time elbow and not NP hard, as it is based on DFS and can be done in order of V plus E time, where V is the number of vertices and E is the number of edges in a graph G. So answer is option C. This question belongs to data structure subject and was asked in GATE CSE 1992. So the question states, a 2-3 tree is such that all internal nodes have either 2 or 3 children. All the paths from root to leaves have the same length. The number of internal nodes of a 2-3 tree having 9 leaves should be 2, 5, 6 and 7 are the options. So we have been given that we have 9 leaves. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So each internal node can either have 2 or 3 children. So let us first see if each internal node has 3 children. Okay. So we need 3 nodes for this, and then we need a node for this. So how many internal nodes do we have? 1, 2, 3, 4. So answer is 4. Let us see if any other arrangement is possible. So we had 3 nodes like this. Now can we have 2 nodes for this? Yes. But here a single node will come. This is not possible. Okay. Which means here only 3 will get connected to over here. Okay. So let us try to change the arrangement downside. Let us try to make some of them as 2 childs. Okay. Let's assume these 2 get connected to 1. These 2 get connected to 1. These 2 get connected to 1. And these 3 get connected to 1. Okay. Now what can we have? These 2 can get connected to 1, these 2 can get connected to 1, and these 2 get connected to 1. What are the number of internal nodes? 1, 2, 3, 4, 5, 6, 7. So 7 is also possible. Let us try to change the arrangement. How can we change it? Let us try to connect these 3 to 1, but here this one will become single, so it's not possible. Okay. Let us try to change it further. Okay, let us assume that these 3 get connected to 1 and these 2 get connected to 1. Again the same arrangement will come, as we can't connect 3 to 1, as this will remain same. So only 2 arrangements are possible, one with 4 internal nodes and one with 7 internal nodes. So answer is option A and D. It was an MSQ type question, multiple select question. This question belongs to engineering mathematics subject and was asked in GATE CSE 1992. So the question states, a non-planar graph with minimum number of vertices has 9 edges 6 vertices, 6 edges 4 vertices, 10 edges 5 vertices and 9 edges 5 vertices. Okay, so if we have the minimum number of vertices, so one vertex is planar, yes. 2 vertices graph is planar, yes. 3 vertices graph is planar, yes. So what is a planar graph? Which means no 2 edges should intersect each other. They should intersect only at the endpoints, not anywhere in between. 4 vertices and 4 edges. Whether it's planar or not, yes, it's planar. Okay. Now let us see 5 vertices. Okay. We have 5 vertices. Okay. Now it's asking the non-planar graph with minimum number of vertices has. If we draw it like this, if we have the K5, which is complete graph with 5 vertices, then what happens? You can see this is a non-planar graph. So answer is 5 vertices and 5 into 4 by 2, which is 10 edges. 10 edges and 5 vertices. Okay. This can also be an answer with minimum number of vertices, 4. But this is planar. So answer is K5, option C. This question belongs to algorithm subject and was asked in GATE CSE 1992. So the question states, following algorithms can be used to sort n in the range from 1 to n cube in order of n time. heap sort, quick sort, merge sort, and radix sort. So what the question is saying is that we have n numbers. We have n numbers such that each number can be in the range of 1 to n cube. 1 to n cube. Suppose we have 100 numbers, then each number can be in the range of 1 to 100 cube. Okay, or we can say 1 to 10 to the power 6. Okay, so what's the complexity? For n numbers, heap sort always take order of n log n, irrespective of the what is the range of each number. Quick sort will take order of n square or n log n, but definitely it can't do it order of n time. Merge sort will take order of n log n every time. Now let us see radix sort. So what is a radix sort? So in radix sort, what we do is we take all the numbers, all the n numbers are taken and written like this. Then we sort the least significant bit first, then the next bit, then the next bit, then the next bit, then the next bit. If we have n numbers such that each number is represented in the base b, and the largest number, as it depends on the complexity of largest number, if the largest number has more bits, then it will take more time. Let us suppose the largest number has d digits. Then what's the complexity of this? Its complexity is order of d into number of numbers plus base b. Okay, then what is this d? Let us suppose k is the largest number. The value of the largest number is k. Then it comes out to be order of, what will be the number of bits in this? Then d is the number of bits. D will be equal to log k base b. So we will have order of log k base b into n plus b. Okay. Now here we are given that the largest number is in the range of 1 to n cube. So it can go at max to log base b of n cube into n plus b. Okay. If we want to reduce it, what value of b should we take? B should be taken as large as possible. So let us take b to be, this 3 will come down, so we will have 3 into log base b n. So b should be taken as large as possible. So can we take b 1? Yes, we can take 2. Yes, we can take. Can we take b as n? Yes, it's our choice. We can take b as n. So we have order of 3 into log base n of n into n plus b is n. So it comes out to be order of 3 is a constant, so can be neglected. Log base n of n is 1. So we have order of n plus n, which is equals to order of n. So complexity is order of n and can be done using radix sort. So answer is option D. This question belongs to operating system subject and was asked in GATE CSE 1992. So the question states, at a particular time of computation, the value of a counting semaphore is 7. Then 20 P operations and 15 V operations were completed on this semaphore. The resulting value of semaphore is 42, 2, 7 or 12. So we have a semaphore. Semaphore is basically used for synchronization problems. We can have binary semaphore, which can have a max value, a value of 0 or 1, or a counting semaphore, which can have any number of values. So here we have been given a counting semaphore with a value S. Semaphore has two operations, wait on S and signal on S. If the S is this semaphore. Wait of S reduces semaphore value by 1 and signal of S increases semaphore value by 1. Wait of S is also called P operation on S and signal of S is also called V operation on S. So we had 7 value. Then we have done 20 P operations. So its value becomes 7 minus 20, which is minus 13. Then we have done 15 V operations. So its value become minus 13 plus 15, which is 2. So the final value is 2 for this counting semaphore. This question belongs to operating system subject and was asked in GATE CSE 1992. So the question states, a computer system has 6 tape drives with n processes competing for them. Each process may need 3 tape drives. The maximum value of n for which the system is guaranteed to be deadlock free is. So here you can do this by 2 methods. So we have 6 tape drives. Let us represent them by this, and each process will need 3 tape drives. We have n processes. We have n processes. What can be the maximum number of n so that it is deadlock free? So we have a formula for this. We have max need of all processes. For the system to be deadlock free, max need of all processes should be less than number of processes plus number of resources. Here what we have, each process has max need of 3. So max need of all processes 3 into n should be less than equal to number of processes n, number of resources 6. So 3n minus n should be less than 6, 2n should be less than 6, n should be less than 3. So the value of n is 2. Let us see it by the second method. So can we satisfy it with one process? Yes, we can give all 3 to 1. Okay, so 1 is allowed. Can we satisfy it with 2 processes? Yes. These 3 can be given to this, these 3 can be given to this. Yes. Now, can we satisfy it with 3 processes? Okay. We think that we can satisfy it. Give first these 3 to this, then these 3 to this, then let the first one complete, then this one can be again given to this. But here it may be deadlock free, but it is asking guaranteed to be deadlock free. Now I can give you a scenario in which it won't be deadlock free. Let us suppose 2 are given to this, 2 are given to this, 2 are given to this, and each of them need 1 extra, so none of them will complete. So thus 3 may get a situation in which we will get a deadlock. 2 will be guaranteed to be deadlock free. As whatever be the case, this 3 will get this, these 3 will get this. So answer is 2. You can do this by any of the 1 methods. This is the logical method and this is the formula based method. This question belongs to operating system subject and was asked in GATE CSE 1992. The question states, which one of the following is an example of a spool device? A terminal used to input data for a program being executed, a secondary memory device in a virtual memory system, a line printer used to print the output of a number of jobs, and none of the above. So what is a spool or a spooling? Spool refers to simultaneous peripheral operations online. So what are peripheral devices? Peripheral devices are like printer, our mouse, keyboard, joystick, etc. So what is spooling used for? Suppose we have a slow peripheral device. If we have a slow peripheral device and a faster application then what happens? Suppose we have a printer, a very slow printer. Printer is generally slow, and a fast interface, like a fast program which gives the print command. So what it has to do if there is no spooling, it will give one command, wait for all the print operations to complete. This program will have to wait. There is wastage of CPU time. Then after the print is done, one is done, it will give the second print command. Then it waits for the program to get printing to get complete. Then it gives the third command and so on. So instead of this, we will have a spool. So spool is basically a queue. Here this program will give faster, at a fast pace, it will give all the commands in the spool. It will be stored in spool. And then after that, it can do its own work and CPU efficiency will increase. And meanwhile, this printer can take the instructions from this spool and do the printing. As these peripheral devices do not need CPU time. Okay. So see, the terminal used to input data for a program being executed. So if we are inputting the data, then this input operation is itself a slow process and this terminal processing is fast. So there is no need of spooling. The secondary memory device used in a virtual memory system. This is not at all related to spooling. A line printer used to print the output of number of jobs. Yes, we use spooling for this as the printing process is a slow process and the software which gives the print command is a faster process and thus it can increase its efficiency by using spooling. None of the above? No. So answer is option C. This question belongs to Theory of Computation subject and was asked in GATE CSE 1992. So the question states, for a context-free grammar, follow of A is the set of terminals that can appear immediately to the right of non-terminal A in some sentential form. We define two sets, L follow of A and R follow of A, by replacing the word sentential by left sentential and rightmost sentential respectively in the definition of follow of A. So which are true? Follow of A and L follow of A may be different. Follow of A and R follow of A are always same. All three sets are identical and all three sets are different. Okay, so let us see if we are able to terminate some of the options by taking an example. Let us assume the following grammar: S implies AB, A implies A, and B implies B. So which string can we derive? Only string derivable is AB from the given grammar. So what is follow of A? So according to the definition, follow of A is a set of terminals that appear immediately to the right of non-terminal A in some sentential form. Okay, so if we have S derives AB, then this B is reduced to B, then we have AB. So only terminals that appears to the right of A is B. So follow of A is B. Now let us see what is L follow of A. L follow of A. So what is L follow of A? L follow of A is the set of terminals that appear immediately to the right of a non-terminal A in some left sentential form. So let us draw the left sentential form. So in left sentential form, almost the leftmost non-terminal is replaced. So here A is replaced by small a and B, then B is replaced by B. So here we can see no non-terminal appears to the left of A. To the right of A, the right of A, no non-terminals, no terminal appears, only non-terminal is there. So left follow of A is empty or null. Let us see R follow of A. So what is R follow of A? R follow of A is nothing but it is set of terminals that can appear to the right of a non-terminal A in some rightmost sentential form. So let us do the rightmost derivation. So every time rightmost non-terminal is replaced, then A is replaced to capital A is replaced to small a. So here you can see the terminal B appears to the right of the non-terminal A in the rightmost derivation. Thus R follow of A is B. Okay. So here you can see that L follow of A is not equals to the follow of A. This is not equal to follow of A. So all three can't be identical for sure. L follow of A and follow of A may be different. Yeah, it can be different. Okay. So A is true. Okay. It may be a MSQ type question. So let us analyze all. Okay. And all three sets are different. Let us see this. Here you can see follow of A and R follow of A are same. So all three sets are different is also false. All three sets are identical is also false. Follow of A and L follow of A may be different. Okay. Now let us see follow of A and R follow of A are always same. We can't say always same by just an example. We need to prove this, whether it's always same or not. So let us see how we can prove this B part. Okay. So see. Okay, so what is follow of A? In follow of A, we will get all the terminals which appear to the immediate right of A in some sentential form. What is R follow of A? In here we do the rightmost derivation, here we do any derivation. Any derivation, and all the terminals which appear to the immediate right of A in the right sentential form is called R follow of A. Now see, since a right sentential form is also a sentential form, it's just a derivation can be leftmost derivation or a rightmost derivation. Thus, rightmost derivation is also a derivation. Thus, we can say we can say that R follow of A is basically a subset of follow of A, as rightmost derivation is also a derivation. Okay. Now to prove that both of them are equal, we need to prove that what we need to prove? We need to prove that follow of A is a subset of R follow of A. This one we need to prove. This one is already proved. This one we need to check whether it's true or not. Okay. So how will you check this? Okay. So let us assume that let a terminal T can appear to the immediate right of a non-terminal A in sentential form. Okay, so how you will do this? Any terminal which can appear on the immediate right of a non-terminal in some sentential form must also appear to the immediate right of the same non-terminal in the right sentential form. Let us suppose we have a non-terminal and we have a terminal over here. If this happens in any sentential form, then it must also happen in the rightmost sentential form. Let us assume a terminal T can appear to the immediate right of a non-terminal A in sentential form. In which case can this happen? Either T is already in the grammar, like T is already there in the production like this, S implies AT, or T is produced by some reduction, like if we have S implies AB something like this, and we have B implies T, which means T is produced by some production. Okay, now since we are looking at the immediate right terminal in sentential form, it means leftmost derivations cannot produce the terminal we need. See, we are looking at the immediate right. So which means the leftmost one cannot produce them. The leftmost one cannot produce the terminal, since here A will be reduced before we do the production. Thus, leftmost we have nothing to do. Either it is already present. If it is already present, then it will also be in the rightmost derivation. And if it is derived, then it will always be derived in the rightmost part first. Thus, we can see that follow of A will always be a subset of R follow of A. And this one we have proved, as A is a subset of B and B is a subset of A, thus A equals to B. So both option A and B are true. This question belongs to compiler design subject and was asked in GATE CSE 1992. So the question states, consider the SLR1 and LALR1 parsing tables for a context-free grammar. Which of the following statements are true? So it is an MSQ type question. Multiple answers can be correct. The go-to part of both the tables may be different. The shift entries are identical in both the tables. The reduce entries in the tables may be different. The error entries in the tables may be different. Okay, so all the LR parsers. Now LR parsers can be LR0 parsers, SLR1 parser, LALR1 parser, and CLR1 parsers. So all the LR parsers differ in the placement of reduce moves. Okay, and the shift entries are same for all of them. We have the same shift entries. Or shift moves are same in all LR0, SLR1, LALR1 and CLR1 parsers. Okay, and even the go-to entries, same shift entries and go-to entries are same for all of them. They differ only in the reduce entries. Now let us see the reduce entries. In LR0 item, we place the reduce moves in entire row of final item. Okay, in LR1 item, we place the reduce moves only in follow of LHS of final item. Okay, in SLR1 parsers, in CLR1 parsers, what we do? This LR0 parser, SLR1 parser, and this is CLR1 parser. In CLR1 parser, we place the reduce moves only in look ahead of final item. Okay, and the last one is LALR1 parser. In LALR1 parsers, we place the reduce move in all the merged look ahead for the final items. Okay, in all the merged look ahead of final item. Thus, all of them will have different reduce entries, but shift and go to entries will be same. Let us see the options. The go to parts of the table may be different. No, go to part is always same. The shift entries are identical in both the tables. Yes. SLR1 and LALR1 have same shift entries. Reduce entries may be different. Yes, we can have different reduce entries because in SLR1 we place the reduce moves only in the follow of LHS of final item, and in LALR1 we place the reduce moves in merge look ahead of final item. Thus, reduce entries may be different. The error entries will always the error entries will also be the different. Why error entries will be the different? Because they will have different because of conflicts. The error entries will be different. So answer is option B, C, and D. This question belongs to engineering mathematics subject and was asked in GATE CSE 1992. So the question states, which one of the following predicate calculus statements are valid? So let us see each of the statements one by one. So we have for all x, px, or for all x, qx is true. Okay, then this implies for all x, either px is true or qx is true. Okay, now let us analyze this statement. What this is saying is that if we have some set x with the items a, b, c, and d, if for all these items px is true, or if for all these items qx is true, then if we take then for all x, which means for all the items either px is true or qx is true. Let us consider the example that px means it is divisible by 3 and qx means it is divisible by 2, and let us take x to be 3, 6, 9, 12. Then for all x, px will be true as all of them are divisible by 3. But for all x, qx won't be true as items like 3 and 9 are not divisible by 2. But for all x, for each item, either p will be true or q will be true. As for 3, it is divisible by 3. 6 is divisible by 3, 9 is divisible by 3, 12 is divisible by 3. So this is a true statement. Let us see option B. So option B states, option B is there exists an x such that px is true and there exists an x such that qx is true. Then it means there exists an x for which both px and qx is true. This one is false. You can easily see. Suppose px means divisible by 3 and qx means divisible by 3. Okay, and x has items like 3, 6, 9. Okay, what this means? It means there is an item which satisfies divisibility by 3. Yes, 3 is divisible by 3, 6 is divisible by 3, 9 is divisible by 3. So this is true. This one may be true or may be false, but for this example, this is true. There exists an x such that qx is true, which means divisible by 2. Yes, 6 is divisible by 2. Okay. Oh, okay, or let us do one thing. If we want to make this as false, let us take only items 3 and 9. Okay, there exists an item such that it is divisible by 3. Yes, both 3 and 9. So this is true. There exists an item such that it is divisible by 2. Okay, is there any item which is divisible by 2? Okay, so let us take 4 over here. Yeah. Yes, 4 is divisible by 2. So this is true and this is true. Okay, both of them are true. So does this implies that this is also true? This means it should be divisible by 3 and divisible by 2. Whether 3 is divisible by both 3 and 2? No. 4 is divisible by both 3 and 2? No. 9 is divisible by both 3 and 2? No. So this is false. A is true, B is false. Let us see option C. Option C says for all x, px is true or qx is true. Okay, then this implies for all x, px is true or for all x, qx is true. It means if for all the items either p is true or q is true, then it means p will be true for all the items and q will be true for all the items. This is false. You can easily take an example. Let us assume p is divisible by 2 and q is divisibility by 5, and we have items like 2, 4 and 5. Then for all x, either p is true or q is true. Yes, 2 is divisible by 2, so p is true. 4 is divisible by 2, so P is true. 5 is divisible by 5, so Q is true. Which means for all items, either P is true or Q is true. And this one means for all items, either P is true, or for all items, Q is true. Which means P should be true for all of them. No, as 5 is not divisible by 2. Q is true for all of them. No, as 2 and 4 are not divisible by 5. So this one is also false, this one is also false. So this statement is not valid. So option C is also false. Let us see option D. So option D states there exists an X such that either P is true or Q is true. Okay. Then it means it is not true that for all X, Px, or there exists an X, Qx. Okay. So what is this saying? This is saying if we have something like we have a bracket over here only. Okay. Yeah. So if there is an X such that for it either P is true or Q is true, then it shouldn't be true that for all X P shouldn't satisfy, or there should be an X for which Q should satisfy. Okay. So let us assume that for all X Px is true and Qx is not true for any X, which means for all X Qx is not true, which means Px satisfies for all X and Qx doesn't satisfy for any X. Then see whether left will be true or not. Whether there will exist an X for which P is true, yes, P satisfies for all X's. So we can take any of the X and make left hand side as true. Okay. Now what will be its value? As P satisfies for all of them, so it will be true. Negation of true will be false. So we will get over here false. Or whether there exists an X for which Q is true? No. There exists no X for which Q is true. So it will come out to be false. So true implies false. Thus it is also not valid. So answer is option A is only valid. This question belongs to engineering mathematics subject and was asked in GATE CSE 1992. So let's see what the question states. Which of the following are a tautology? A or B implies B and C. A and B implies B or C. A or B implies B implies C. A implies B implies B implies C. So how can we expand A implies B? A implies B is equivalent to negation of A or B. So let us try to expand each one of them. What is the meaning of tautology? Tautology means it is true for all values of A, B and C. So A will expand like A or B implies B and C. So applying this formula we will get A implies B equals to, or let us take it like X implies Y, so that it do not create any confusion. So if we have X implies Y, then it's equivalent to negation of X or Y. So this is X, this is Y. So we will have negation of X or Y. Y is B and C. Okay. So what is this? Expanding this, we will get negation of A, or will become and negation of B, and or B and C. So we will have something like this. Now what we can do? Now let us try to see whether it's true for all the values of A, B and C or not. So let us try to make this as false. So if we take C as false, this becomes false. Okay. And if we take A as true, A as false, B as true, and C as false, then let's see what happens. Negation of false is true, true and negation of B. Negation of B is false, true and false is false, false, or B is true, true and false is false. So false or false is false. So it comes out to be false only. Okay. As here A or B, it will come out to be a true. True implies B and C, which comes out to be false. So yeah, this will come out to be false. So this is not a tautology. And let us see option B. So option B states A and B implies B or C. Let us apply this formula. This comes out to be x and this is y. So we have negation of a and b or b or c. So we have negation of a or negation of b or b or c. So negation of b or b is always true. So we have negation of a or true or c. True or anything is always true, so it comes out to be true. So this is a tautology. Let us see option C. So option C states A or B implies B implies C. Okay. So if we expand the second implication, we will get negation of B or C. Now if we expand this, we will get negation of A or B or negation of B or C. So we will get negation of A and negation of B or negation of B or C. Okay. Or let us take it like this only and try to make it false. So if we need to make it false, we need to make any of the side as false. Okay. Okay. We want to make this side as false. So if this side should be false, both sides should be false. If we want to make this as false. If this side should be false, then A should be true. Okay. B should be true. So that true or true comes out to be true and negation of true is false. Okay, we will get false. But here, what is B? B is true. Negation of true is false. Okay. C should be false. Okay. So we will get false, or if we take B as true. Okay. So these are the values. A should be true, B should be true, and C should be false. The negation of true will comes out to be false. False or false is false. So false or false is false. So this is not a tautology. Let us see option D. Option D states, okay, so we have A implies B implies B implies C. Let us expand the last implication. So we get negation of B or C. Let us expand this implication now. We have A implies negation of B or negation of B or C. Okay. Now let us expand this implication. We get negation of A or negation of B or negation of B or C. So if we want to make this complete as false, then A should be true. So that negation of true comes out to be false. B should be true. So that negation of true comes out to be false. If B is true, negation of true is false, and C should be false. So that we get false or false is false, false or false is false. So this is also not a tautology. So answer is option B. This question belongs to Theory of Computation subject and was asked in GATE CSE 1992. So the question states, which of the following regular expressions identities are true? Option A, R bracket whole star equals to R star. This is clean closure of R, clean closure. There is no significance of writing the clean closure in a bracket. So both of them are equivalent. Let us see option B. Option B says R star S star equals to R plus S whole star. Thus RHS is nothing but its sigma star, which means all the possible strings over R and S. And what is LHS? LHS means R should come previous to S, or S should only come after an R. So this LHS can't generate strings like SR, SS, RR, SR, SR. So it can't have the strings in which any R comes after an S. So these are not equal. Let us see option C. So option C is R plus S whole star equals to R star plus S star. So the LHS is sigma star, which means all the possible strings over R and S, and RHS it can generate only strings containing any number of R, like sigma, R, double R, triple R, or strings containing any number of S, like sigma, S, double S, triple S, but it can't generate strings which have a combination of R and S, like SR, RS, SRS, S, SRR, etc. So these are not equal. Let us see option D. Option D, it's LHS means all the strings in which S comes after R. And RHS have all the strings of either R or S. So it can't generate. See, LHS will have strings like RS, RS, double S, triple R, triple S, double R, 4 times S. But LHS can't have strings with a combination of R and S. It can either have only R's or only S. Thus, these are also not equal. So answer is option A. This question belongs to Theory of Computation subject and was asked in GATE CSE 1992. So the question states, if G is a context-free grammar and W is a string of length L in L of G, how long is the derivation of W in G if G is in Chomsky normal form? Okay, so we have been given a grammar G, which is a context-free grammar, and it is in Chomsky normal form. So a grammar G is said to be in Chomsky normal form if it has productions of the form A implies BC, A implies A, and S implies epsilon. This is present only if epsilon belongs to language of a grammar, where A, B, and C are belongs to non-terminals. A belongs to terminal and S belongs to start symbol. Okay. Then we have, okay. So if the language is represented by L of G and we have a string W which belongs to L of G, then how long will be the derivation of this W in G if the length of the length of W is L, then how long will be the derivation? Okay, let us analyze this. Suppose we start from a non-terminal A and then we do A implies. So suppose we have initially A, then we replace it by A implies BC, so it becomes BC. Okay, then we can again replace this by 2. So if we can replace it by another 2, which means at each replacement we are increasing the length by 1, and we need to go to the length of L. So how many replacements do we need to do? Initially we have a length of L 1, and we need to just do L minus 1 replacements, as it will increase the length by L minus 1, and total length will become L plus L minus 1, which is L. Okay, and then we will have all A1, A2 up to AL, we will have all non-terminals. Then we need to use this second production to convert all of them to the terminals. So L production rules need to be applied. So we need to apply L more production rules. So what is the total length? This was initial, and these many derivations we have done. So what is the length of derivation? It's L plus L, 2L minus 1. So we have 2L minus 1 length of the derivation of W in G. So answer is option C. This question belongs to Theory of Computation subject and was asked in GATE CSE 1992. So the question states, context-free languages are closed under union, closed under complementation, closed under intersection, and closed under clean closure. It is a multiple select type question, MSQ question. So for these type of questions, I have already told you that you need to remember just this table and you can solve these questions. So context-free languages are closed under union, yes, under intersection, no, under complementation, no, under clean closure, yes. So answer is option A and option D. Being closed means if we have two CFLs L1 and L2, then the union will always be a CFL. L3 will always be a CFL. Being not closed means if we have a CFL, let us suppose CFL1, then if we do its complement, then its complement is if equals to CFL2. If it is equals to L2, then L2 may or may not be CFL. It can also be a CFL, but there is no guarantee that it may be a CFL. It can or cannot be a CFL. So answer is option A and D. Just remember this table. This question belongs to Theory of Computation subject and was asked in GATE CSE 1992. So the question states, in which of the cases stated below is the following statement true? So we have a statement given. For every non-deterministic machine M1, there exists an equivalent deterministic machine M2 recognizing the same language. Options are M1 is a non-deterministic finite automata, which means NFA. M2 is a non-deterministic PDA, which means NPDA. M1 is a non-deterministic Turing machine, which means NTM. For no machines and in M1 and M2, the above statement are true. So in which case can we say a non-deterministic machine NM1 is equals to its deterministic equivalent DM1? This means here if these are equivalent, which means for every NM1 we can get a DM1 and for every DM1 we can get a NM1. This happens only when their power is same. See, the power of NFA is equals to the power of DFA, which means they represent the same set of language. If we have a DFA for a language, we will have a NFA, and we can convert, if we have a NFA, we can convert the NFA to the DFA by some algos, and we can get a DFA for the language in polynomial time, of course. Then we have, so option A is true. M1 can be a deterministic finite automata DFA, as we can have an equivalent NFA, as we can have an equivalent DFA for it. M2 is non-deterministic PDA. See, for PDAs, the power of non-deterministic push-down automata is not equal to the power of push-down automata, deterministic push-down automata. Why? Non-deterministic machine push-down automata has more power than deterministic push-down automata. See, if we have some strings like palindrome, palindromic strings, palindrome, even palindrome, let us consider, over English alphabet, WWR. Then the example of a palindrome is ABAB, then BABA. So at each step, we have to make two decisions. Either we should, then we will push to the stack. So for each item, we need to make a decision. Whether we need to push it to the stack or this is our middle item, we need to start popping. Like either we should push it or we should start popping. Like suppose we get A over here. Now top is B, so we will push it. Now we get B. Then we have to make a decision whether we want to pop it by matching to the top of the stack or we want to push it. Let us suppose the string was something like this: A, B. Then we have double A, 4 times B, double A. Okay. Then we push A. Then on seeing next day, we have to make a decision whether this A should be matched with this A and popped or it should be pushed. This can't be done by a deterministic machine. This has to be done by non-deterministic machine. So we need a non-deterministic push-down automata for palindromes. And its power is more than deterministic machine. As it can have more transition. It can make choices at a step. Whether to push to the stack or to pop an equivalent item from the stack. Thus, M2 can't be a non-deterministic push-down automata as it has more power and a language which is it is possible that a language is accepted by non-deterministic push-down automata and we can't get a deterministic push-down machine for it. M1 is a non-deterministic Turing machine. See, for non-deterministic Turing machine, its power is equivalent to a deterministic Turing machine. So option C is also true. For no machines M1 and M2, the above statement is true. This is false as it is true for NFA as well as the Turing machines. So answer is option A and C are true. This question belongs to computer organization subject and was asked in GATE CSE 1992. So the question states, which of the following macros can put a macro assembler into an infinite loop? So we have macro M1 and a macro M2. Second only, first only, both first and second, and none of the above. Let us understand a few lines. So what does this line mean? Macro M1 comma X, which means this is a macro with X as a parameter. Macro M2X, which means this is a macro with X as a parameter. Similar to our functions, if we take a function with F with A as a parameter, then similarly F is synchronous to M and A is synchronous to X. If EQX, if X equals to 0, then M1 X plus 1. It is checking if equal, it is checking the value of accumulator with the value of X, and it is true if X equals to 0, which means for a value of X equals to 0, we will call M1 X plus 1. It is similar to writing if A equals to 0, then call the recursive function f with A plus 1, which means it is again calling the function. Okay, let us see this one. It is a function with A as a parameter, M2x. If EQx, then it calls M2x, which means it checks the value of x against some value, and if that value is true, it again calls, if checks the value of A against some constant, and if it is true, then it again calls f with the same value. So here you can see, as here we are changing the parameter from A to A plus 1. Thus this recursion will keep on going and will terminate at some base condition. But this recursion will keep on going. Again it will call, see, FA will call FA, then again this FA will again call another FA. So we will have something, a loop like FA calling FA again and again. So this will lead to an infinite loop. So second will lead to an infinite loop, first one will not lead to infinite loop. So answer is option A, second only. This question belongs to computer organization subject and was asked in GATE CSE 1992. So the question states, mention the pass number for each of the following activities that occur in a two-pass assembler. Object code generation, literals added to literal table, listing printed, and address resolution for local symbols. So what is the step for compilation? Suppose we have a .c file, which is high-level language file. First it is given to compiler. Compiler converts it into assembly level language. Then it is given to assembler. Assembler converted into 01 or the low level language. Okay. So this assembling process is basically done in two passes. Okay. Why is it done in two passes? Because like suppose we have certain mnemonic codes for jumps. Like on a conditional jump we have jump to an address, that is suppose X, and we have certain instructions, if instruction, go to instructions. Okay, now when these go to and jump instructions came, then they have a corresponding address to them. During the forward pass we do not know what is the actual value address at which this X is present. So we first make a one pass and then we do the back patching in the second pass, which means after the first pass we store that X was mapped to, let us suppose, 2008 address in hexadecimal. Then in the second pass we replace this X by 2008 in hexadecimal. This is called backpatching. So thus we need two passes of our assembler. Now in two passes various things are done. Let me show you what all things are done. So see here, during the first pass what all we are doing, we are assigning the address to all the statements. So whatever statement we have go to statement, we have certain if statements, we have jump statements, we have move statements. So we assign address to all of them, 1000, 1002, 1004 and so on. Okay, we save the values. If we have certain variables, we save the values. Processing the compiler derivatives, we have certain assembler derivatives, we process them. Table creation, we create a table for like this X and we add the literal to that table. Allocating space for literals, we allocate the space for these literals and compute the total length of our program. Okay, so what all is done in the first pass? Object code creation is done in the first pass. Literals are printed in the first pass. Okay, now let us see what all is done in the second pass. Sorry. Listing adding to literal table is done in the first pass. Here it is written. Let me first clear this out and then show you. Okay, so object, let us first see task performed in second pass. Generating object code, we generate the object code. For this the corresponding 01 code is generated in the second pass. So object code generation done in pass 2. Writing, printing, assembly, listing. So listing is printed in the second pass. Address resolution is done in the first pass as writing the address for all the statements. And then literals are added to the literal table. Here we have adding literals to the literal table is done in the first pass. So answer is 2121. Statements A and C are done in the second pass and statement B and D are done in the first pass of the compilation. This question belongs to data structure subject and was asked in GATE CSE 1992. So the question states, how many edges can be there in a forest with P component having n vertices in all? Okay. So we have a forest with P components. P components means it will have P parts. Okay, so total number of vertices are n, and we have P components, which is component 1, component 2, so on up till component P. Each component should be a tree. So let us suppose we have x1 vertices in component 1. So number of vertices are x1. Let us suppose we have x2, so on up till xp. So as there are total n vertices, so x1 plus x2 up till xp should be equal to n. Okay, now let us see. Each component should be the condition for a forest is that each component should be a tree. So if we have a tree with n vertices, let us write it over here. Tree with n vertices has n minus 1 edges. As each component need to be a tree, thus the number of edges in this will be x1 minus 1, this will be x2 minus 1, and this one will be xp minus 1. So number of edges, we can write it as E equals to, it is equals to x1 minus 1 plus x2 minus 1 up till xp minus 1. Let us expand it. So let us take all the x terms together. xp minus 1 minus 1 minus 1 up to p times. So this value equals to n. So we have n minus 1 p times equals to 1 into p. So we have number of edges equals to n minus p. So the answer is n minus p. So if we have a forest with p component having total n vertices, then the number of edges is n minus p, as each component should be a tree, and a tree with x1 vertices has x1 minus 1 edges. So answer is n minus p. This question belongs to data structures and algorithm subject and was asked in GATE CAC 1992. So the question states, assume that the last element of the set is used as partition element in quicksort. If n distinct elements from the set 1 to n are to be sorted, give an input for which quicksort take maximum time. Okay, so what is quicksort? So in quicksort, first partitioning is done. Then we apply quicksort on the left side, and we apply quicksort on the right side. Okay, quicksort is initially applied on the full input. Okay, so the complexity depends on the size of this left and right part, which in turn depends on the partitioning. Okay, so suppose we have n items and they are sorted in ascending order, like 1, 2, 3, 4, 5. Let us assume 10 items, 6, 7. Okay, let us take n. So here the last item is taken as pivot. It is given over here. Assume that the last element of the set is used as partition element. Okay, so what we do, we take the last item and we make sure that all the items to the left of, on the left of it are less than it, and on the right of it are greater than it. So thus we will have all the items from 1 to n minus 1 on its left and nothing on the right. Then again n minus 1 is taken as pivot, and we will have all the items on the left of it as this, and on the right nothing. So if we have Tn as the total complexity, then partitioning always takes order of n. Okay, then the left side will have t n minus 1 items, and the right side will have 0 items. T0 is 1, so it can be neglected. So Tn equals to t of n minus 1 plus n. You can solve it and you will get order of n square. Okay, now let us see the second case, when they are sorted in descending order. So we have n, n minus 1, n minus 2, then 3, 2, 1. 1 is taken as pivot, last item. All the item on left of it are less than 1, and on the right of it are more than 1. So nothing comes on the left, and all the items n, n minus 1, n minus 2 up to 3, 2 comes on its right, not necessarily in the same order. Now again, this last item 2 is taken as pivot, nothing comes on the right, and nothing comes on the left, and everything comes on its right. Same is followed. So the complexity is same. Tn equals to n for partitioning and n minus 1 items on its right and 0 items on its left. So complexity comes out to be order of n square. So we got two cases, which means sorted, ascending or descending. Then it will take the maximum complexity. If they are randomly sorted, then we can assume that Tn equals to, if we do the partitioning, then half of the items come on the left and half will come on the right. So we will have Tn by 2 plus Tn by 2. So we will have complexity as 2Tn by 2 plus n, which comes out to be order of n log n. Okay, but this is not the maximum time. Maximum times comes when it is sorted in ascending or descending order. There can be another case when we have same items. Then also the complexity, like we have all 2's. And if last item is taken as pivot, then everything on it left should be less than or equal to any condition that you take. Less than equal to, so all n minus 1 items will come over here, nothing on the right. Same goes in the next condition also. So same items also have order of n square complexity, but the question itself says we should have n distinct items. So only cases sorted in ascending order or descending order, and the complexity is order of n square. This question belongs to operating system subject and was asked in GATE CSE 1992. So the question states, which page replacement policy sometimes leads to more page faults when size of memory is increased? Optimal, LRU, FIFO, or none of these? So we have certain pages reserved for, we have certain main memory frames reserved for a particular process. So if we have a process can have many pages. This is the virtual memory, but our main memory has only a few frames fixed for that process. Let us suppose this has only 4 frames. Now if we increase the number of frames to 1, 2, 3, 4, 5, then common sense says that we should lead to less page fault, as here there will be less chances of page fault as more pages can be accommodated. But there are some algos in which the number of page fault increases while increasing the number of frames. So those algos are FIFO, first in first out, second chance, and random algo, random page replacement algo. And this phenomena of increasing the number of page fault on increasing the number of frames is called Baladi's anomaly. Okay, now see, there is a property called stack algo. So what is a stack algo? Let us assume that these are the frames, and at various instances it has different pages. Like suppose P1 was here, then P2 comes, P1, P2, then P3 came, P1, P2, P3, and so on. Now if we increase the number of frames to 5, 1, 2, 3, 4, then it will also have some pages, P1 over here, P2 over here. So stack algos are those algos in which all the pages in the first part is a subset of the second part. Okay, and these algos will never suffer from the Baladi's anomaly, and in these algos always the page fault will reduce. So what are those algos? Those algos are optimal and stack based algo. Optimal and LRU, least recently used algo. So these algo do not suffer from Baladi's anomaly. No Baladi's anomaly. No Baladi's anomaly means less page fault on increasing number of frames, because these are stack algo. These algos are called stack algo, in which at each point, like this one P1 should be a subset of all of them which are present in this on increasing. So let me again revise you all the concepts. So generally the number of page faults should reduce, but page fault increases. Why it increases? They increase due to a phenomena called Baladi's anomaly. It occurs in FIFO, second chance, and random page replacement algorithms. Now this anomaly do not occur in stack based algo. What are stack based algo? In which at each point Lesser one should be a subset of larger one. So it occurs in optimal and LRU. They do not suffer from Bellardi's anomaly, and the page fault reduces on increasing the number of frames. So the question was asking which page replacement policy leads to more page fault on increasing the size of memory, which means which page replacement suffers from Bellardi's anomaly. So answer is FIFO, second chance and random. So we have FIFO over here. So answer is option C. This question belongs to Digital Logic Design subject and was asked in GATE CSE 1992. So the question has three parts. Let us see all of them one by one. Part A states, consider addition in 2's complement arithmetic. A carry from the most significant bit does not always correspond to an overflow. Explain what is the condition for overflow in 2's complement arithmetic. Okay. So if we have been given two numbers A and B in 2's complement arithmetic and we perform the addition of A as well as B, then we get some output. In these cases, an overflow always, if we have a bit coming out of this last bit, the carry from most significant bit does not always guarantee an overflow. There is a condition for overflow. We can say that the overflow equals to, if we have a bit in the last significant bit, C in is the carry in the last significant bit and C out is the carry from the last significant bit, most significant bit. Then XOR of C in, XOR C out will tell us whether overflow is there or not. If its value is 0, then it means no overflow. And if its value is 1, which means overflow is there. Okay. Now let me show you with the help of an example. Consider we have two numbers 1 0 1 0 1 1 1 1 0 1 0 1 and we perform addition. Then 1 plus 1 is 0, carry over 1, 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 1 plus 1 plus 1 is 1, carry over 1. So what is C out? C out is 1. What is C in? C in is 1. So 1 XOR 1 is 0. 0 means no overflow. So no overflow in this case. Let us take another example. 0 1 1 1 1 1 plus 0 0 0 0 0 1. 1 plus 1 is 0, carry over 1. 1 plus 1 is 0, carry over 1. 0 carry over 1. 0 carry over 1. 0 carry over 1. It's 1 and carry out is 0. So C out is 0, XOR C in is 1. So 0 XOR 1 is 1, which means there is overflow in this case. So the overflow condition is C in XOR C out. Now let us see B part to this question. So part B states, a priority encoder accepts three input signals A, B and C and produces 2-bit output x1 and x0 corresponding to the highest priority active input signal. Assume A has the highest priority followed by B and C has the lowest priority. If none of the inputs are active and the output should be 0, 0, design the priority encoder using 4x1 multiplexer as the main component. So we have to design the priority encoder for this. Okay. So let us assume MSB is the most significant bit and LSB is the least significant bit. So what should be the truth table for A, B and C? So the truth table should look something like this. Then we have MSB and LSB. What all combinations can we have? We can have 8 combinations 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1 with all ones. Okay. Now see. If we have all zeros, then it is given that the output should be 0, 0. Okay. If we have 0, 0, 1, then C has highest priority as of now. So answer should be 0, 1. Okay. If we have 1, if B is 1, then C do not matter. It should be don't care. And here the answer should be 1, 0 for both of them. Okay. Now if A is 1, then B and C don't matter and answer will be 1. Okay. So what does 0, 0 indicate? 0, 0 indicate which means all are zeros. What does 0, 1 indicate? 01 indicates C has the highest priority as of now. 10 indicate B has the highest priority as of now, and 11 indicate A has the highest priority as of now. Now let us draw the K maps for this. So K map will look something like this. We have A, B, C, and three inputs: A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Now we have for MSP, it will first of all let us create for MSP. So MSP has 1 in 0, 1, 0, okay, 0, 1, 0, 0, 1, 1, and 1, 0, 0, 0, 1, 1, 1, 1, and this. So we will get two mappings. First one is this, and second one is this. So answer for MSP will be MSP equals to, so what will it be equal to? It will be equal to, this one will be equal to B, and this one will be equal to A. So we will have A plus B. Okay. Now let us draw the K maps for the LSP. So K map for LSP will look something like A, B, C, and A, B, C inputs. A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So it will have 1 in the fields 0, 0, 1, then all these 4. So we will have two pairings, one is this and one is this. So LSP will be A plus B complement C. So we got the MSP and the LSP. Now we need to design it using our 4x1 mux. So how can we design it? Okay, so let us take a 4x1 mux over here. Okay, it will have input 0, 0, 0, 1, 1, 0, 1, 1. Another 4x1 mux can be taken over here. It will have input 0, 0, 0, 1, 1, 0, and 1, 1. It will have two select lines S0 and S1. This one will also have two select lines S0 and S1. So S0 is connected to A and B. S0 is connected to A, okay, over here and over here. And S1 is connected to B, over here and over here. So we have S0 and S1. C is connected to this 0, 0 input. Okay, this one is given as 0, this one is given as 1, this one is given as 1, this one is 0, this one is 1, this one is 1, and this one is 1. So this signifies the MSP output. This is the MSP output, and this signifies the LSP output. Okay, now let us verify the outputs. I will show you how these outputs can be easily verified. Okay, so see, first of all, what's the truth table for this one? So for MSB, we will have something like when both the inputs are 0. So let us assume MSB output. When both the inputs are 0, S1 complement and S0 complement and S1 complement. What is S0? A complement, B complement. Then output is this 0. So we got 0. When S1 is 1 and S0 is 0, which means A complement B, then we get output as 1. When we have AB complement, then we have output as 1. When we have AB, then we have output as 1. Okay. Now let us try to simplify it. Let us take A as common. Let us do it like this: A complement B complement plus A complement B. Let us take A as common. We get B plus B complement, which is equals to 1. So we get, this is 0, so this will cancel out. So we'll have A complement B plus A, and now we have a theorem. So how the theorem goes like? Theorem goes like, if we have x plus x complement y, then it is equals to x. I can prove it for you. Suppose we have x over here, we can write it as x into 1. Now 1 plus anything is same, so we can write 1 plus y plus x complement y. So we can have x plus xy plus x complement y. We can have x plus, taking y as common, we will have x plus x complement. X plus x complement is 1, so we'll have x plus y. So this is equals to, sorry, x plus y. So this one will be equals to, this is x complement, this is y. So it will be equals to a plus b. So MSB is verified, a plus b. Okay. Now let us verify LSB. LSB can also be verified in a similar manner. Let me show it to you. So we have LSB equals to, when S1 and S0 both are 0, which means A complement, B complement, we get C as output. When A is S0 is 0, we get 0 as output. When S0 is 1 and S1 is 0, we get 1 as output. When both are 1, we get 1 as output. So this one will cancel out. We will have A complement, B complement, C plus, taking A as common, we will have B plus B complement. B plus B complement is 1, so we will get LSB equals to A complement B complement C plus A. Taking this as X, this as X complement, and this as Y, we get X plus X complement Y equals to X plus Y. So we will have X plus A plus B complement C. So LSB is also verified. So this is our answer. This is done using two 4 cross 1 muxes. Now let us see option question C. So question C, let me first clear the screen out. Okay. So what is our question C? Question C states, design a 3-bit counter using D flip-flops such that not more than one flip-flop changes state between any two consecutive states. Okay, which means when we are transitioning from state A to state B, only one flip-flop should change its value. Okay, so it is actually similar to gray code concept. If we start with 000, the next state will be only change of one bit, which is means 001. Next will be 011. Next will be 010. Next will be 110. Next will be 111. Next will be 101. See, every time only one bit is changing. This one is changed to 0. Then we have 100. This one is changed to 0. Then this one is changed to 0. Now let us draw the table for this. So table for this. This is a 3-bit synchronous counter. So we have present state and then we have next state, or we can say flip-flop inputs. Okay. So flip-flops are DA, DB and DC. So if we have, and present state is ABC. So we will fill the same. If present state is 000, what's the next state? Next state is 00111. So we have, wait, for 001, let us start from here. From 001, next state is 011. For 000, next state is 001. For 010, 010, then we have 011, then we have 100, then we have 101, then we have 110. For this, the next state will be 110. For this, the next state will be 010. For next one, it will be 000. For next one, it will be 100. Next one, it will be 111. This one we filled from using this. Let us see, suppose for 111, next state is 101. So for 111, it should be 101. Okay. And what about, let us see for 100. For 100, the next state is 000. Next state is 000. Now let us draw the K map for this. So K map for A, B, and C. Okay. So we have 2, 3, 4. We have variables A, B, and C, 00, 01, 11, 10, and 01. So the values are 1 for, let us draw it first for DA. So the value is 1 for which values? DA has 010, so for 010, for 101, 110, for 101, 101, 110. Okay, and do DA have anyone? Yes. What will be the value for 111? I guess we have missed 111. For 111, the answer should be, what's the next state of 111? 101. Okay, so we have missed 111. Yeah. So for 111, it will have also 1. So for 111. Okay. So this will be one mapping. This will be one mapping. So what will be DA? DA equals to AC plus BC complement. Okay. Yeah. Now let us draw for DB. So let me first complete this up. Yes, for DB it will be DB has value 1 for 001, 001, for 010, 010, 011, 011, and for 110, 110. Okay, so the mapping will be like this, and DB will have a value A complement C plus BC complement. Now let us fill it for DC. Okay, let me draw the table again. So table is 1 for 001, 000, 110 and 111, 111 and 110. Okay, so this is one mapping, this is one mapping. So DC will come out to be A complement B complement plus AB. So what is it equal to? It is equal to A XOR B. Okay. Now let us draw a diagram. So we have the expression and we can easily get the diagram. See, this is DA, this is DB, and this is DC. It will get A as output, B as output, C as output. All of them will have a single clock as these are synchronous counters. Okay, we will have clock over here. Now let us see what is DA. It's AC plus BC complement. So it's AC plus BC complement. We'll have A over here, C over here, B over here, C complement over here. We can use a directly C and then a NOT gate to get C complement also. Then we have an OR gate over here and DA over here. For this we have A complement C plus BC complement. So same goes over here. We can use a NOT gate also, A complement C plus BC complement, NOT gate here too. Then we have an OR gate and this goes to DB. Then for this we just have an XOR gate with the inputs as A and B. So this is our answer to the third part. So we have done all A, B and C parts. This question belongs to operating system subject and was asked in GATE CSE 1992. So the question states, the access times of the main memory and the cache memory in a computer system are 500 nanosecond and 50 nanosecond. So what is main memory access time? It's 500 nanosecond. What is cache memory access time? It's 50 nanosecond. It is estimated that 80% of the main memory requests are for read, which means read request, like for an instruction, it is a probability that with a probability 0.8 it will be a read, and with a probability 0.2 it will be a write. 20%, or we can say 0.2 probability, it is with 0.8 probability. Okay, now rest are for write. The hit ratio for the read access only is 0.9. So read hit ratio is 0.9. So what is read miss ratio? Read miss ratio is 1 minus 0.9, which means 0.1. With a probability of 0.1, a read will be missed, and with a probability of 0.9, a read will be a hit. Now see, write through policy is used, which means both cache and main memories are updated simultaneously. Okay, write through policy. So what does this mean? Let me explain it to you. Determine the average time of the main memory. Okay, so what is I will explain what is average main memory time. So what all operations we are performing? We are performing just read and write operations. So it is equals to read time plus write time. Okay, now what can happen? Suppose this is our CPU. It generates an instruction and this is our main memory. First cache memory will come, then we will have main memory. Okay, what is the probability of getting a read instruction? So let us break it down. Read, hit, either it can be a read hit or it can be a read miss, or it can be a write hit, Like we were writing, but we got a hit in cache. It was a write instruction, but we got a miss in cache. So we need to bring the block from the main memory. So what is the probability of a read instruction? It's 0.8. Okay. What is the probability of it being a hit? Read hit is 0.9. So it is 0.9. Now, what is the time taken? So what happens? It was a read instruction and we found it in the cache. So what is the time taken? It is equal to the cache access time, which is 50 nanosecond. Okay. Now we have plus read miss. What is the probability of read? 0.8. What is the probability of it being a miss? 0.1. What is the time? If we get a miss in a cache, then we bring the block from the main memory to the cache. So time equals to main memory access time plus cache access time. Here we have assumed this hierarchical organization. Either we can have hierarchical organization or simultaneous. Like simultaneous, both main memory and cache memory. But as nothing is written, thus we assume hierarchical read as default. Hierarchical read is as default. And simultaneous write is given. But read we assume hierarchical as it is a default thing. Now what is the probability of being a write? It's 0.2. What is the probability of write being a hit? So we have with a probability of 0.9, it will be a hit. And if write is a hit, then what is the time taken? Suppose we have a write instruction and it is a hit, which means we found it in the cache. Then what happens? We have to update it in the main memory. So what is the time taken? Time taken is 500 plus. What is the probability of it being a miss? 0.2 for write, 0.1 for being a miss. Now if it is a miss, now we have simultaneous write policy. Simultaneous write means main memory and cache are updated simultaneously. So instead of 500 plus 50, both will update simultaneously and we will take max of both, which is 500. So we will have 500. So let us calculate this. This will be 36 plus 44 plus 90 plus 10, which is equals to 180 nanoseconds. So this is our answer. The average time for main memory access is 180 nanoseconds. This question belongs to algorithm subject and was asked in GATE CSE 1992. So the question states, consider the function fn for which the pseudocode is given below. So this is our function fn. So this is the definition of the function. We have begin followed by end. Then first we create a variable f1 and assign a value 1 to it. Then if n equals to 1, then the value of f we store as 3. Else we take a loop from for i equals to 1 to n, begin, end. In the loop we do c equals to 0 and for j equals to 1 to n minus 1, begin, c equals to c plus 1, end, and f1 equals to f1 into c, where n is a positive integer greater than 0. Then it is asking derive the recurrence relation for fn. Now see, what is recursion? Suppose we have a function n with some parameter n. In recursion, in the body we are again calling the same function with a different parameter. Let us suppose n minus 1. This is recursion. But here see, inside fn we are never calling f with the same or different parameter. There is no call like fn into 2 or fn minus 1 inside this body. So it is not at all a recursive function. So we can't write recurrence relation to it. So here not possible to write recurrence relation for f of n. Okay, if it had been recursion, we can easily write the recurrence relation. Now let us see option B. Option B says solve the recurrence relation for the closed form solution of fn. So there is no recurrence relation, so we can't solve it. But we can get a closed form solution for fn. It is basically asking what this question is, what this code is actually computing. So let us see what this is computing by analyzing it. Okay, so see what it is doing. Initially we are having this body, we have begin followed by an end. So we will create a variable f1 and assign a value 1 to it. So if n equals to 1, then f will have a value 3, which means if n equals to 1, then Fn equals to 3. Else, when f is not 1, then we will take a loop from 1 to n, and inside the loop we are creating a variable c with 0, and for j equals to 1 to n minus 1 we are incrementing c. See this loop. In this loop, we are taking a loop from j equals to 1 to n minus 1 and incrementing c. So at the end of this loop, every time c will have a value n minus 1. So we can replace this entire code by c equals to n minus 1. And after this, what we are doing? We are just multiplying f1 by c. So in one iteration, what we are doing? We are having a value of f1 as 1. We are multiplying it by c n minus 1. Okay, c is n minus 1. Then the next iteration, again we are calculating c to be n minus 1. Then we are again multiplying it with f1. So this gets multiplied with n minus 1. How many times? N times, as this loop is running n times. Okay, so what is the value of f1? F1 will have a value n minus 1 to the power n. So the answer to this is n minus 1 to the power n. Else fn equals to n minus 1 to the power n. So this is our closed form solution to this, what this code is computing. So we can't write a reconciliation, but we can get a solution what fn is representing. So fn is representing a value 1, 3 for n equals to 1, and else it is computing n minus 1 to the power n. This question belongs to algorithm subject and was asked in GATE CSE 1992. So the question states, let T be the depth first tree of an undirected graph G. So we have an undirected graph G and we have a DFS of that, which is a tree T. T is a tree. An array P indexed by the vertices of G is given. P of V is the parent of a vertex V in T. Parent of root is the root itself. Give a method for finding and printing the cycle formed if an edge uv of G not in T, i.e. edge belongs to G minus T, is now added to T. Okay, so now what this is saying is that for this graph we will have a DFS tree. We will have a DFS tree called T. It won't have any cycle. The tree will look something like this. It won't have any cycle. Now suppose give a method of finding and printing cycle formed if an edge uv of G not in T. If now it is saying if we add a edge, let us suppose this edge is added which is not in T. If a new edge is added which is not in T and E belongs to G minus T, which means the edge which was not present, then we need to find and print this cycle. We need to actually print this cycle. This one over here, this cycle. We need to print it. Okay. Time taken by a method must be proportional to the length of the cycle. Describe an algorithm in Pascal C-like language. Assume that the variables have been suitably declared. Okay, so we basically need to just give an algo. So see, how can we do this? Suppose we have a graph like this. Okay, we can take any graph. Okay, let us assume it's vertex 1, 2, 3, 4, and let us take this as vertex 5. Or let me use a different color so it do not make any confusion. It is vertex 1, 2, 3, 4 and 5. So what is the DFS for this? DFS of this will look something like, there can be many DFS. Let us take any one DFS like this one, 3, 4, and then I should connect this. So any edge can connect. Let us assume this one will connect this. Now it is saying if we add a new edge, let us suppose this edge is added. This is a new edge added. Then we need to detect this cycle. Which cycle we need to detect? 1, 2, 3, 5, 1. This cycle we need to detect by an algo. So how the algo will go like? I will write the algo over here and demonstrate it to you on the left hand side. So what we will do? Initially we will mark all vertices with let us assume green color is given with green color, with blue color. Okay, let us assume with blue color. We mark all the vertices with blue color. Let us assume white only, with white color. White color. Okay, so all the vertices are initially white. Now start DFS from any vertex. Okay, let us assume we start from 1. Okay, so we start from 1. Okay, now if vertex is white, white means non-visited, then make it any other color. We can assume, make it blue, make it blue and push to stack. Okay, so we have a stack. So what we will do, we will make this vertex as blue, so 1 is made blue and push to stack. So we will have a blue vertex 1 over in the stack. Okay, now what we will do, go to neighbors, of this new vertex. Okay, so we go to any neighbor. So either we can go to 5 or we can go to 2. Let us assume we go to 2. Now again this vertex is white, so we make it blue. So this is made blue and push to stack. So we have 2 over here. Now we can go to any neighbor. Let us assume we go to 3, make it blue as it is white and push to stack. Now we go to the next neighbor, either 4 or 5. Let us assume we go to 4, make it blue and push to stack. Now there is one more condition. If no neighbor make it black and pop from stack. So 4 do not have any neighbor, so we color it black. So this one is colored now black, not blue, and we pop it from the stack. 4 is popped from the stack. Okay, now where we go? We go to the stack top 3, its neighbor. Any unvisited neighbor it has? Yes, it has 5. Okay, so we go, make it blue and push it to the stack. Okay, now any other neighbor it has? Yes. Now there is another condition. If we encounter a blue neighbor, then cycle detected. See, what does this blue mean? Blue means it has already been visited, which means we have come back from another part to the same vertex. So 1 is already visited, which means a cycle is detected. Now stack contents are nodes in cycle. So what are stack contents? They are 5, 3, 2, 1. So there is a cycle 1, 2, 3, 5. 1, then 2, 1, 2, 3, 5, and then again 1. So this is our cycle. Now what we need to do? We need to make sure that it runs in according to the length of the cycle. Okay. So let us see the complexity. Suppose we have v vertices in this. Now when we create a tree, then tree will have how many edges? It will have number of edges equals to v minus 1. Now we are adding an extra edge, so number of edge becomes equals to v. This TFL will have number of edge equals to v and number of vertices equals to v. And what is the complexity of DFS? It's order of number of vertices plus number of edges. What is number of edges? It's v. So we get order of 2v, which is equals to order of v. So it is approximately equal to the length of the cycle. So we have got our algo. This is our algo. This is our complexity. This question belongs to programming subject and was asked in GATE CSE 1992. So the question states, what type of parameter passing mechanism, call by value, call by reference, call by name or call by value result, it is call by value result, is the following sequence of actions trying to implement for a procedure called PI, where P is a procedure, I is an integer and A is an integer array. So we have a procedure P which takes parameters A of I, where this A is an array, I is an integer. So this procedure has the following contents. Create a new local variable z, so it creates a variable z, assigns the value z to A of I, okay. So it does like this. Execute the body of p using z, then it uses z in the entire function, and then set a of I to z. So see carefully, what is it doing? It is creating a new variable and making changes in the new variable and then updating the original variable. So it is equal to call by value result. So what call by value result does? Call by value result creates a variable, updates the variable, and then at the end it just copies the value to our initial variable. So it is call by value result. The implementation is correct. Now let us see part B. So part B states, show the activation records and the display structure just after procedures called at the lines marked X and Y. So here we have line Y and line X. We need to tell what are the various activation records at these points have started their execution. Be sure to indicate which of the two procedures named A you are referring to. So we have to tell which of the procedures of A we are referring to. So for this, assume we have A1 and A2, and we have B1 and B2 be the different instances of A and B. So let us iterate each of them one by one. So how it happens? Here, first of all, we will come to this test part. So here, activation record will just have test because test started. Okay. Now, when this, we will come to this scope of A started. So now activation record will have test followed by A. Okay. Now the scope of B started. Scope of B is from here till here. Scope of A is from here till here, and test is from here till here. Okay. Now let us see. Now inside B again A started. So first let us write it for B started. Test, then A started, then B, let us assume a new instance B1 started. Now what happens? Now this A started, so the instance that started is A1. Test A, B1, then A1 started. Okay. So A1 does its computation, then A ends. So when A ends, this A1 gets pops out. So here we have just test A and B1. Now what happens? Now again Y calls A. So what happens? We create a new instance A2. So we have test A, B1, A2. So A2 is created. Now A2 does its work and then it pops out of the stack. So A2 is then removed from the stack. So we just have test A and B1. Now what happens here? B also ends. So when B ends, then this B gets removed from the stack. Activation record stack. Okay. Now what happens? Then this A begins. Okay. So what we have done? Here see. After this, B starts and ends. Okay. Then after this ends, A also ends. So A gets ended. So we just have test over here. So test is just over here. Now what happens? Then it calls A. So an instance is created which is for A. So we just have test and A. So this was the activation record through the entire procedure calls. This question belongs to compiler design subject and was asked in GATE CSE 1992. So the question states, write syntax directed definitions, which means SDD or the semantic rules, for the following grammar to add the type of each identifier to its entry. So what is an SDD? SDD is nothing but there are some rules written to the right of the grammar to check for the semantic correctness of a program. So we are for the grammar to add type to each identifier to its entry in the symbol table. So we have to write the semantic rules to define the type of each of the identifier during semantic analysis. Rewriting the grammar is not permitted and semantic rules are to be added to the ends of production only. Okay. So see carefully this statement. What this is saying? Rewriting is not allowed, which means we have to use the same grammar and semantic rules are to be added to the ends of production only. So what it means? This means that this is an S attributed grammar. Okay. And S attributed is a subset of L attributed. Thus it is also an L attributed grammar. Okay. And if it is L attributed grammar, which means it will have inherited attributes. which means the values can be inherited from the parent or left sibling. Left sibling only. Now let us write the production rules. So how can we write it? So here let us start from the end. So here we have L implies IT. So first of all we have to enter the type. So we will say enter type. We will take id.entry as a parameter and L.in. This L is an inherited attribute. Now what we have to do? We have to do L implies L comma ID. So what can be the rule for this? The rule for this can be, first of all we will enter the type. So we will have enter underscore type. We will take id.entry and L.in. And then we will assign this L to this L. So we will have L1, we will create a new instance, L1.in equals to L.in. Okay. Now what is the type of this? So we will have t.type is real. What will be the type of this? We will have t.type equals to integer. Type equals to integer. And what is the type for this? So type for this will be, which we are performing these operations. So this operation can be performed only when both the types are same. So it will be L.in equals to t.type. Okay. So this is our solution to this. Now let us see the second question. So the second question states, write 3 address intermediate code, which means quadruple codes for each of the Boolean expression in the sequence as it would be generated by the compiler. Partial evaluation of Boolean expression is not permitted. Assume the usual rules of precedence of the operator. So this is our expression. We need to write the quadruples. So what is the meaning of quadruples? Quadruples means we will have 4 fields, which means each operation, each instruction will have 4 fields. What will be those 4 fields? The operator. Let me create the table for you. It would be much easier. So each instruction will have an operator. It will have an argument 1. It will have an argument 2. And it will have the result. Quadruples means which we have 4 addresses: operator, argument 1, argument 2 and result. Now we will fill this table. Okay. Now this is our expression: a plus b greater than c plus d, or a greater than c, or and b less than d. So how can we express this? Let us assume we take t1 to be a plus b. We create temporary variables and we take t2 to be, let me write it over here only. Okay, let me assume t1 to be a plus b, t2 to be c plus d. So how this becomes equivalent to, it will have t1 greater than t2, or let me assume t3 equals to let us take a greater than c and b less than d. Now we can take t1 greater than t2 to be a new variable. Let us assume t3 equals to t1 greater than t2. So it got again reduced to t3 or a less than c. So we can take t4 as a less than c, a new temporary variable. So t3 or t4, and we can have t5 as b less than d. Okay, so it will have t3 or t4 and t5. Now we can have an expression for this. We can assume t6 equals to t4 and t5. So it becomes equivalent to t3 or t6, which can be again stored in another variable t7. So t7 is t3 or t6. So this is our quadruple representation. Now let me write it in the form of table. So first of all we have the operator plus. Argument 1 is a, argument 2 is b, and the result is stored in t1. Then we have c and d as argument with the operator plus and stored in t2. So first is done, second is done. Then for third we have the operator greater than, the arguments are t1 and t2 and the result is stored in t3. Then we have this, result is stored in t4, the inputs are taken from a and c and the operator is greater than. Sorry, I think here it's greater than, and here it's less than C. Okay, now we have the result in T5. We have the operators B and D, arguments, and the operator is less than. Then we have T4 and T5, and the operation is and the result is stored in T6. Then we have result in T7. The arguments are in T3 or T6, and the operator is OR. So this is our table for this. So this is the answer for the first question, and this is the answer for the second question. This question belongs to operating system subject and was asked in GATE CSE 1992. So the question states, draw the precedence graph for the following component program given below. So this is a program and we need to draw the precedence graph for this. See here, we have certain statements, pair begin, parent, begin, and end. So all the statements between begin and end have serial execution. Serial execution means the next statement will be executed only after the previous statement has executed. Then we have statements like pair begin and parent. So the statements which are between pair begin and parent, they have parallel execution. Parallel execution means anyone can execute first. They can execute in any order. So I will show you this. So first of all, we have this serial execution of S1 followed by S9 with pair begin and parent in the middle. So we have initially S1 will execute, at the end S9 will execute, and we will have this pair begin and parent statements in between. Now see, in between pair begin and parent, we have this begin end, and S7. So this means this first begin end will execute, then second begin end, they can execute parallelly. The first, second, and third statements can execute parallelly. So we can have S7 or the second part or the first part. Anyone can execute first. Now let us break down the first part. So first part is between begin and end, which means they must execute serially. So we will have S2 followed by S4. Now let us decode the second part. So second part has begin with S3, pair begin parent followed by yes. So first of all, which means first S3 would be there, then this pair begin parent part will be there, and inside this S5, S6, S8 can execute parallelly. So we can have either S5 or S6 followed by S8. So this is our statements, and we can have S9 after any one of them. So it goes on like this. So initially we will have S1 followed by S2, S3, S7, then we have S4, S5, S6 followed by S8 and S9 at the end. Now let us see the second part of the question. So question 2 states, let the page reference and the working set window be. So we have certain page references, page reference string. So our string is CCDBCECEAD. Let us cross verify CCDBCECEAD. Okay. And we have working set window size. So we have window size as 4. So why is this working set algo used? Working set algo is used when we want to give this random pages, random frames to a certain process. Like sometimes it may be process we need only 2 frames, sometimes we may need 3 frames, sometimes we may need 4 frames. So at max we can give 4, but when there is no need we can also give lesser frames. The initial working set at time t equal to 0 has the pages A, D and E. So we have initial working set is our ADE, which means initially only A, D and E 3 frames are present. So initial window size. What is initial window size? It is 3. With A being referenced at t equals to 0, D being referenced at t equals to -1 and E being referenced at t equals to -2. Which means E is the oldest one and A is the newest one. Determine the total number of page faults. So we need to tell number of page faults. and the average number of page frames used while computing the working set at each reference. Okay, so let us draw the table for this first. So table will have certain entries. So what are those entries? We have a time, like at last t at t equal to 0 a came. So it will start, time will start from 1. We have working set, window. So initially it had A, D and E at time 0. So we need to maintain a notation. Let us assume the newest one is kept on the right. So we had A, then before this T, then before this E. We have whether it is a hit or a miss. Okay, as we need to count the number of page fault. Then we have current window size. So what was initial window size? It was 3. Now let us compute the things out. Okay, so what is our, okay, so initially C will come. Okay, so let us also make an entry for incoming page entry, like which is the page that is coming. So initially C is coming at time t equals to 1. So what will be our working set? We have E, D and A. Its size is 3 and max size it can go is 4. So can we accommodate one more? Yes. So we will have E, D, A and C. Okay. Whether it is a hit or a miss, it is basically a miss. So M represents a miss. So what is our current window size? It comes out to be 4. Okay. Then what is at time 2? What comes at time 2? We have another C. Okay. So what our window becomes? We can remove this E. So we'll have D, A and C, and it is actually a hit. Why is it a hit? It is a hit because C is already present. So it is a hit. Window size is 3. Yes. Now let us see the third one. Third time D comes. So D comes at time 3. Whether it is a hit? Yes. So we need to keep D at the most frequent position. So D comes to the last position. It was a hit, and window size, what is our window size? Window size is 3. Now we have B. Whether it is a hit or a miss, it is a miss at time 4. So what our window becomes? Our window becomes C, D and B. We pop out this A and B comes up. So what is our window size? Window size is 3. Now what happens? What is our next frame? Next is C page. Whether it is a hit or a miss, it is a hit as C is present. What is the time? Time is 5. What our window set becomes? D, B, C is the most frequent one, so it comes at the end. What is our window size? Window size is 3. Now what is the next one? Next one is E. At time 6, we have D is done, C is done, now E is being done. At time 6, whether it is a hit or a miss, it is a miss as E is not present. So what our window becomes? It becomes D, B, C and E comes at the end. So what is our window size? Window size comes out to be 4. Now what happens? Now C comes at time 7. C is a hit. So we have a hit. So what happens? We pop out D and C comes at the end. B, C and E. Okay. And it was a hit. What is our window size? Window size is 3. Now what comes next? Next is E. Time is 8. So T is a hit. So we just have C and D and we pop out B. It was a hit and window size is 2. Now what happens? Now we get a A. So C is done, E is done. Now we get a A at time 9. So what our window become? We push A. Window size is 3 and it is a miss. Now at end we have D. It is also a miss and our window becomes C, E, A, D. Window size is 4 at time t equals to 10. Okay. So what are the number of page faults? Page fault occur for a miss. So 1, 2, 3, 4, 5. So we have number of page fault equals to 5. What are average number of frames? So let us sum this up. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 4, 20, 23, 25, 28, 32. So we have 32 divided by 1 up to 10, which means 10. So number of average page frames are, average number of page frame is 3.2. So answer is 5 and 3.2, and this is the answer for the A part. This question belongs to database management system subject and was asked in GATE CSE 1992. So the question states, how is redundancy reduced in the following models? Hierarchical, network and relational model. Okay, so if we have a database which is basically a collection of files, then we can store these files in various methods. These three are those methods: hierarchical, network and relational. In GATE syllabus, you just have the relational model. Now it is asking, how can you reduce redundancy in the following model, which means how can you reduce redundancy in relational model. So in relational model, what you do is store the data in the form of tables. Okay, you use tables to store the data. Now redundancy occur when the same data is present over multiple tables. So you can use the normal forms, which means you can convert a relation to BCNF, which is Boyce Codd normal form, 3NF, 2NF or 1NF if you want to reduce the redundancy. BCNF has the least redundancy and 1NF has the most redundancy. So we can use normalization or the normal form concept to reduce the redundancy in the relational models. Now let us see option B. Suppose you have a database consisting of the following three relations. So we have relation frequents, which has fields customer and hotel. Okay, we have another serves, which has field hotel and snacks. So serves table basically consists of names of hotel and what snacks they serve. And we have likes, and frequents has which customer visit which hotel frequently. Likes has customer and snacks. It tells which customer like which snack. Okay, so the first indicates the hotels each customer visit, the second tells what snack each hotel serves, and the last indicate which snacks are liked by each customer. Express the following query in relational algebra. So this is our query. Print the hotels that serve the snack that customer Rama likes. So we have a customer Rama, we need to print the hotel name which serves the snacks liked by Rama. Okay, so first of all let us try to write the SQL query for this. So how can we write SQL query? What we need? We just need select s.hotel. We just need the hotel names. From what do we need hotel names? Okay, so we need to do the cross product of serves table renamed as S, likes table renamed as L. So what all do they have common? They have common snacks. So where s.snacks equals to l.snacks, and we have customer name in L. So we will write l.customer equals to Rama. Okay, so this will give our answer. This is the SQL query. So how can we now write? We need to tell what is the relational algebra query. So how can we write relational algebra query? Let us convert this SQL query to relational algebra query. It's very easy to convert. It's logical also. So what is we have this symbol for selection. What we need to select? We just need to select the hotel names. So pi hotels. This is our selection. This is our projection. What we need to project. Now what we need to select? We need to select based on the thing where customer name equals to Rama. So customer equals to Rama. And what we need to do? We need to do the cross product, conditional cross product. Okay, so see, this likes table has snacks and serves table has snacks. So we can also do the natural join. Natural join joins directly based on the common attribute, which is snacks over here. So we will do likes natural join serves. So what it does? It does the conditional join based on the common attribute, or this is called natural join. So this whole thing this thing is being taken care by the natural join of serves and likes, and we write this condition in this selection, and we write this select condition in this projection. So this is our answer: pi hotel sigma customer equals to Rama likes natural join serves. This question belongs to engineering mathematics subject and was asked in GATE CSE 1992. So the question states, if G is a group of even order means it has even elements, or we can say 2n elements, then show that there exists an element A which is not equal to E, where E is the identity element in G, such that A square equals to E. So if E is the identity element of the group, if E is identity element, then we need to show that there exists an item element A such that A square equals to E, such that A is not an identity element, which means A is anything apart from that identity element. So how we will show this? So here we can do it by contradiction. We can do it by contradiction. Assume that there is no element such that there doesn't exist any element such that A square equals to E, which means A square is not equal to E for any element A belongs to our group. Okay, which means then what is the meaning of A square is not equal to E? Let us multiply A to the power minus 1 on both the sides. So A to the power minus 1 not equal to E into A to the power minus 1. So which means A to the power 1 is not equal to A to the power minus 1, which means for a non-identity element A. So what does this mean? This means that the inverse of any element, shouldn't be equal to that element. Shouldn't be that element itself. What happens if the inverse of an element equals to itself? So which means if x equals to x inverse, we can multiply x on both sides, so we will get x square equals to E, and this fails our contradiction. So this shouldn't happen. Okay, now let us see what we can do. Okay, so we have to actually get at least one element has its own inverse. If we can found an element which has its inverse equal to itself, like x inverse equals to x, then we can show that this assumption is wrong, this assumption is wrong, this assumption is wrong, thus our contradiction is wrong. So we have to just find an element whose inverse equals to that element. So what is our aim? Our aim is to find any one element whose inverse is itself the element. Okay, we need to just find that element. Okay, so how we will do this? So as G is a group of even order, so let us assume number of items in G is 2n. Now take the identity out of this. So if we take identity out of this, if we take B minus E, why we take identity out? Because we know A shouldn't be equal to E. So we take the identity out, so we just have 2n minus 1 items. So we need to deal with this 2n minus 1 items and find an item whose inverse is that item itself. So how we will do this? So let us assume we got an item x such that x inverse is not equal to x, which means it is satisfying our contradiction. Then what we will do? If we found any item, if inverse of x is not x and it is something like x inverse is y, then what we will do? We will remove x and y. X and y will be removed from these 2n minus 1 items. Okay, which means if any item satisfies our contradiction, then 2 items will be removed. Okay, from these 2n minus 1 items, each time we will remove 2 items. Whenever an item satisfies our contradiction, our claim, we will remove 2 items. So how many items do we have? We have 2n minus 1 item. It is an odd number, which means if all the items satisfy our contradiction, then at the end we will remain with 3 items. Then 3 minus 2, we will remain with 1 item. So at the end we will be left with just 1 item. Now we know this item, let us suppose it's Z. then its inverse should be that one only. Why? Because it cannot map to the inverse of any other item. Like z cannot be mapped to y, x or any other item, because inverse is always unique. And inverse of this z inverse can't be equal to the identity element. Why? Because inverse of identity is identity itself. Which means if we had 2n minus 1 item and we keep on satisfying a contradiction and removing two items, then we are left with a single item, and inverse of that single item should be itself only, because its inverse can't be any other item and its inverse can't be identity, because identity inverse is identity inverse, identity only. Thus we got an item with z inverse equals to z. Thus if we multiply z on both the sides, then what we get? Z inverse into z equals to z into z. So we get z square equals to e. So we have got an item such that a square equals to e. So this was our proof for the first part. Now let me just clear the screen out and show you this proof for the second part. So it was just a proof based question. It came in GATE CSE 1992. Now theoretical explanation questions do not come, but it can give you a base for like how can we prove the things out. So let us see what is our second question. So second question states, consider the set of integers 1, 2, 3, 4, 6, 8, 12, 24 together with two binary operations LCM, which is lowest common multiple, and GCD, or we can say SCF, greatest common divisor or highest common factor. Which one of the following algebraic structures does this represent? Group, ring, field and lattice. Okay. Now let me first tell you what all these things are. So what is a group? Group means it should satisfy closure property, associativity property, existence of identity, and existence of inverse. What is a ring? Ring means ring is an item with two operations, like let us assume a plus and star. Then what it means? A plus, a comma plus should be an abelian group. And a comma star should be an semi group, and star should be distributed over plus, which means it should follow distributive property over plus. And what is a field? Field is also defined on two operations, that is assume a plus and star. Then any thing is a field, which means a plus should be an abelian group, and a comma minus with a star should be an abelian group, where E is the identity element. And same like star should be distributed over plus. Okay, now let us see. So what is an abelian group? Abelian group is nothing but group with commutative property. Okay. Now see, if we can prove that something is not a group, if something is not a group, which means it do not satisfy closure, associative, existence of identity and existence of inverse, which means it won't be an abelian group. Okay, it will imply this, that it is not an abelian group. If something is not a group, then it is not an abelian group, because abelian group is group plus commutative property. If it is not an abelian group, then it means it can't be a ring. And it can't be a field. Okay, so let me write it over here. If it is not a group, then it implies it's not a field and it's not a ring. Okay, now let me clear these things out and explain it to you further. Okay, so what is this operation? So we can easily see that this operation is nothing but it is basically our D24 comma divide. This is nothing but D24 comma divide lattice. So what is the meaning of D24 comma divide? Over partial order relation, divisibility, ability. Okay, where D24 indicates positive integral divisors of positive integral divisors of 24. So let us try to draw the map for this. Okay, so map for this will look something like this. Here we have 1, then we will have 2. I will explain you this map. 2, 3, then we have 4, we have 6, 2, 6, 4, 12, then we have 8, and we have 24. Okay, so see what this map indicates. So this map indicates that if the item which is least upper bound is our, if we have 2 and 3, then its least upper bound is 6, which is our LCM. Okay, so least upper bound is nothing but it's our LCM. And what is our greatest lower bound? Greatest lower bound is our GCT. So see, two items, and pick any two items, 2 and 3. What is their upper bound? Upper bound is everything. 6 is an upper bound. If you can match these lines, like 4 can't be, 12 is an upper bound, 24 is an upper bound. What is least upper bound? It's 6. So LCM of 2 and 3 is 6. What is lower bound? Anything below 2 and 3. So 1 is a lower bound and greatest lower bound is 1. Let us assume 8 and 24. What are lower bounds of 8 and 24? 8, and we have 4, then we have 2, and we have 1. What is our greatest lower bound? It's 8. So highest common factor is, or greatest common divisor is of 8 and 24 is 8. Okay, so this is our map for this. Now see one thing. If we take an item 8, so we can say that, so what is our identity element? Let us find the identity for each. Identity for LCM is 1, because LCM of anything, let us suppose LCM of A and anything is that item only. And what is the identity for greatest lower bound? For this it should be 24, because GCD of any item with 24 will always be that item only, because 24 is divisible by 1, 2, 3, 4, 6, 8, 24. So GCD of 12 and 24 is 12, 12, 6 and 24 is 6, 3 and 24 is 3. Okay, but see whether there exists an inverse of an item or not. So what is the inverse of an item? So inverse means if there exists an inverse of an item X, then LCM of that item, let us assume X, with its inverse is Y, should be the identity element, which should be 1 if there exists an inverse. So let us see whether there exists an inverse for 8. If there exists an inverse for 8, then LCM for 8 with its inverse Y should be 1. LCM should be 1, which means least upper bound should be 1 of 8 with any item. So is there any item with which its least upper bound is 1? No. Least upper bound of 8 with any item. With 24 it's 24, with 12 it's 24, with 4 it's 8, with 6 it is not related. So there is no item we can find, which means 8 do not have an inverse. And even we cannot find any item GCD such that 8 with that item is 24, which means there is no Y, which means there is no inverse for an item 8. So there is no inverse, which means it is not a group, because group has an property that it should have an inverse property, like it should be closure associative, existence of identity, and existence of inverse. So if inverse is not satisfied, then it means it's not a group. So it's not a group. So not a group. If not a group, then I proved that it won't be a abelian group. Thus it won't be a field and it won't be a ring. So it will be a lattice. So answer is option D, lattice. There is another method of doing this where I will tell you the properties of lattice and you can solve it directly without checking for a group. So what is a lattice? Lattice is nothing but, you can write that lattice is a, you can say if it follows commutative property. Commutative property. Commutative property means, let us assume this is LCM and this is GCD. Then we can write A hat B equals to B hat A and A or B equals to B or A. This is commutative property. So can we say that LCM and GCD follows commutative property? Yes. Let us see associativity property. Associativity property. We see A, which means here we just change the brackets, which means it is equal to A hat B hat C and A or B or C is equivalent to A or B or C. Does LCM of three items change? Like let us suppose we have LCM of A and B, then it's LCM with C. Does it matter whether we take A and B LCM first or B or C LCM first? No, it do not matter. You can check it. So it follows associativity property. Third, it should follow idempotence property. These are the properties of lattice. What lattice should follow? So what is idempotence property? Which means if we take LCM and GCD with the same item, then we should get the same item. So what is LCM of, that is LCM of 3 and 3? It's 3 only. What is GCD of 5 and 5? It's 5 only. So thus it follows the idempotence property too. Let us see fourth. Fourth, it should follow absorption law. What is absorption law? Which means A, GCD, A or B should be equal to A and A, LCM, A and B should be A. So let us verify it with the help of an example. So if we take GCD of 8 with LCM of 5 and 10. So what is its value? What is the LCM of 5 and 10? So its LCM is least common multiple. So it should be 10. And what is the GCD of 8 and 10? 8 and 10 has a GCD greatest common divisor. So it follows this property. Both the properties are followed. Thus, you can see that it is a lattice. Okay. Thus, you can either do it by this method or the previous method. This question belongs to engineering mathematics subject and was asked in GATE CSE 1992. So the question states, using modus ponens or resolution to show that the following set is inconsistent. So we need to show that if all of them are true, then it is an inconsistency. So let us prove this. Such that where x and y are universally quantified variables, a is a constant and p, q, r are monadic predicates. So it is given that x and y are universally quantified variables. So we can rewrite the above statement as for all x, qx implies px or negation of ra, and we can write the second statement as ra or negation of qa. Third one remains the same, and for fourth one we can write it for all y, negation of p of y. Okay, we can rewrite the statements like this. Now using universal instantiation, this first let us write this as 1, 2, 3, 4. So using universal instantiation of 1, it becomes 5 like this. Q of A implies P of A or negation of R of A, which means it is valid for any instance where A is an arbitrary constant. Now similarly, this fourth becomes equals to negation of P of A using universal instantiation. Now using modus ponens on 5 and 3. So we use modus ponens on QA implies PA or negation RA, and on 3 is QA. So applying modus ponens, we get the 7th statement, which is PA or negation RA. Then what we can do? We can use resolution on 7 and 2. What is 2? 2 is RA implies 2 is RA or negation QA. So we can use resolution on this, and we can get, we have PA or negation RA, and the second one is RA or negation QA. Okay, so we get PA or negation QA. This is our 8th statement. Now using 6 and 8. So using 6 and 8. If PA or negation QA is true and negation PA is true, then it means negation QA is true. Negation QA is true. Now see, we have negation QA is true and QA is true. So both of them can't be true at the same time. So we can say it is inconsistent. So we have proved inconsistency. Now let us see second part of the question. So what the second part states. So second part says, let S be the set of all integers and let n is greater than 1 be a fixed integer. Define for AB belongs to S a relation such that A is related to B if A minus B is a multiple of n. Show that R is an equivalence relation and find its equivalence classes for n equals to 5. So let Z be the set of integers. So we have Z be the set of integers. And the relation R is defined on Z. R is defined on the set of integers where A is related to B. What is given if A minus B is a multiple of n. So here let us do it for 5, which means A minus B is a multiple of 5. Or we can write A minus B or B minus A, anything we can write B minus A equals to 5k for some integer k. This is our definition of our relation. Okay, now let us show that R is an equivalence relation. So for equivalence relation, we need to prove 3 properties: reflexive, then symmetric, then transitive property. What does reflexive property mean? Reflexive property means A is related to A. So let us prove reflexive property. Reflexive. So we have to prove A is related to A. So we can say, let us check if we have A and B belongs to integers such that A is related to B. Then what it means? It means B minus A equals to 5k according to the definition. Now can we say, if we check if A is related to A, so what is A minus A? A minus A is 0. Can we write it as 5 into 0? Thus it is also a multiple of 5. Thus we can say A is related to A. Let us see for second property, symmetric property. So if A is related, it means if A is related to B, then B should be related to A. So what does A related to B means? It means A minus B is a multiple of 5. It equals to 5k. Can we take minus common? Yes, we can. So B minus A equals to 5k. Okay. So can we write it like B minus A equals to minus 5k? Yes. Can we write it as B minus A? We can take A minus B or B minus A. Let us be consistent with what we have taken initially. Initially we have taken B minus A. Okay. So A related to B means B minus A is a multiple of 5. Can we take minus common? Yes. Minus of A minus B equals to 5k. Can we move minus to that side? Yes. A minus B equals to minus 5k. Can we write k1 equals to minus k? So we will write A minus B equals to 5k1, which means A minus B is also a multiple of 5, which means B is related to A. So thus it satisfies the symmetric property. A related to B implies B related to A. Let us see the third property, transitive property. What does transitive property mean? Transitive property means if A is related to B and B is related to C, then it implies A is related to C. So how will we prove this? So assume we have A, B and C belonging to the set of integers such that A is related to B and B is related to C. This is given to us. Then if A is related to B, then we can write B minus A is a multiple of 5, which means 5k, and C minus B is a multiple of 5, which means 5m for some integers k and m. So we have to check whether A is related to C or not. So for A being related to C, C minus A should be a multiple of 5. So how can we write C minus A? So can we do C minus A plus B minus B? Now can we write it as C minus B minus plus B minus A plus B minus A? Yes, we can write this taking B over there. So can we write this as C minus B is 5m and B minus A is 5k. Taking 5 as common, we get 5m plus k. Thus, we can write C minus A is a multiple of 5. Let us write it as 5x, where x is m plus k. Thus, A is also related to C. Thus, it follows a transitive property, and thus it is an equivalence relation. Now we need to tell what are the equivalence classes for n equals to 5. Okay, we can easily observe that it is for n equals to 5, it is nothing but it is congruence modulo 5. I will show you how. Let us assume we have A, first equivalence class is A such that A belongs to integers such that A mod 5 equals to 0. All the items which have a modulus whose modulus with 5 gives 0 will come to one equivalence class. All the items A such that A belongs to Z such that A mod 5 equals to 1 comes to second equivalence class, A mod 5 equals to 2 come to third, A mod 5 equals to 3 come to fourth, and A mod 5 equals to 4 come to the fifth equivalence class. So we have A mod 5, A mod 5, A mod 5. Because modulus can have only 5 values 0, 1, 2, 3 and 4. So A such that A belongs to Z, A such that A belongs to set of integers, A such that A belongs to set of integers. So this is our equivalence class for n equals to 5, which means the results can be broken down into 5 classes. So these are our solutions. This question belongs to Theory of Computation subject and was asked in GATE CSE 1992. So the question states, which of the following 3 statements are true? Prove your answer. It is a MSQ type question. So part A is the union of two recursive languages recursive. So if we have a recursive language, which means we have a Turing machine for it. So if we have two recursive language R1 and R2, so what we can do, let us assume R1 has a Turing machine TM1 and R2 has a Turing machine TM2. Then we can basically combine TM1 and TM2 in our module, and given an input, we can tell yes or no whether that input is accepted or not. So we can just combine the two Turing machines. So this one will also be a Turing machine, and thus union of two recursive language is also recursive. So option A is true. Let us see option B. Option A is true. So option B states the language 0 to the power n where n is a prime is not regular. So where n is prime. So what are the contents of this? We can see 2 is a prime number. So we have 0 square, 3 is a prime 0, 3, 0, 5, 0, 7, 0, 11 and so on. Can we write a C program? Yes, we can write a C program for finding prime numbers, and we can write, thus it is a CSL language, but it is not a CFL. For this, you can do it by using pumping lemma. Pumping lemma for regular language you can use to prove that it is not regular. You can basically go to this link. This is a Stack Overflow link. It shows that how to prove that a to the power p where p is prime is not regular. You can basically follow this link and you can get the pumping lemma proof for the same. So this is also true. It's not regular. Let us see option C. So option C says Regular languages are closed under infinite union. Okay. So are regular languages closed under finite union or not? Let us suppose we have regular language R1 which accepts A square, R2 which accepts A4, R3 which accepts A5. So we have DFAs for this, like we have A followed by A, then accept. Same for A4 we can create, same for A5 we can create. Like for A4 it will look something like A, then another A, then accept. Then for A5 we can also create, and we can create trap states too. From here we can have a trap state on any number of A's. From here we can have a trap state on any number of A's. And for A5 also we can create similarly. So what we can do, we can just combine them to get for the union of these languages. Like we can have something like, if we have A over here, then another A, then we will just accept. And if we have two A's, then a third A, we come over here, then a fourth A, we come over here, then a fifth A also we accept, and a fourth A also we accept. So if we have something like 1, 2, 3, the fourth A we accept, then a fifth A also we accept. Then after this, any number of A's, we go to the trap state. So we can basically also do for finite union. But can we do for infinite union? No, we can't do for infinite union. I will give you an example for that. Let us assume we have a regular language L1 which accepts AB, L2 which accepts A square B square, L3 which accepts A cube B cube. Till these are finite, we can union them. But if it is infinite, then Ln accepts An Bn. So what is the general term for this? It accepts all the strings of the form Ai Bi. But for this, it is a context-free language, because we need to keep track of number of A's and then match it with number of B's. So we need a stack for this, because we will be pushing up A's and then popping B's, A for every B, and then matching whether we reach an empty stack or not. Thus it is a CFL. We need a stack and not regular. Thus infinite unions are not regular. So regular languages are not closed under infinite union. So this is false. So true statements are option 1 and 2.